A very good evening to one and all present in the virtual meet. With immense pleasure and pride, on behalf of Department of Electrical and Electronic Engineering, Krishnasamy College of Engineering and Technology, I warmly welcome you all to the AECT Atal sponsored 6th-day online faculty development program on emerging trends in digital twin technology for hydrogen production, storage, and transport. Now, it is my proud privilege to invite Engineer V. Vetrichelvi, Assistant Professor, Department of Electrical and Electronic Engineering, to invite today's third session chief guest. Ma'am, please.
Thank you, sir. It is our privilege and honor to introduce our chief guest, Professor Vasudevan Subramanian, distinguished scientist at the CSIR Central Electrochemical Research Institute, CECRI, and professor at the Academy of Scientific and Innovative Research, New Delhi. Professor Vasudevan sir is a highly accomplished scientist with over 3 decades of experience in research, teaching, and academic leadership. His pioneering work has made significant contributions in the area of water electrolysis, green hydrogen, water treatment technologies, inorganic chemicals, and energy storage batteries. He has played a vital role in the development of advanced electrolyzers, electrocatalysts, and electrochemical water treatment systems, and has successfully transferred several cutting edge technologies to industries. An outstanding researcher, Professor Vasudevan sir has authored more than 120 research publications and holds over 20 patents to his credit. His assiduous involvement in research and electrochemistry earned him Doctor of Science, and he has been ranked among top 2% of scientists worldwide by Stanford University for 5 consecutive years. He is a fellow of several prestigious national and international scientific academies and serves as a visiting professor at leading institutions. In addition to his scientific achievements, he has contributed significantly to academic administration, having served as a officiating vice chancellor of Madurai Kamaraj University. He also plays an important role as an associate editor and editorial board member of reputed journals, including Scientific Reports, Nature. We are truly honored to have Professor S. Vasudevan sir with us today as our chief guest. On behalf of Krishnasamy College of Engineering and Technology, I warmly welcome you, sir. Please.
Thank you, ma'am. Thank you for your wonderful introduction. I invite our today's guest, Professor S. Vasudevan. Sir. The session is handed over to Professor S. Vasudevan. So please, sir.
I am audible. Are you able to hear my?
Yes, sir, you are audible, sir.
Thank you very much for this wonderful opportunity. Almost more than 100 participants are there. First of all, the organizers, it is a time to conduct this type of webinars to share or to enrich the knowledge of to everyone. So now I am sharing my this one. Are you able to see my slide?
Yes, sir.
Yes. Thank you very much. Today, my talk is based on green hydrogen, the silent backbone of the cleaner future. That is in energy sector and environmental sector and the climate. So always the student has a vision to velocity. So this is the concept. Everyone to keep this vision to velocity. So why hydrogen? We are talking last I think last 5 decades we are talking on hydrogen. So this is because the hydrogen has been described as a Swiss Army knife. So that means the hydrogen will be used for everywhere. The applications are wide. So you can see that no, this is no Swiss Army knife. So everyone may be seeing that. So the multiple things are there. So like the Swiss Army knife, the applications of hydrogen will be the wider, like no in the case of chemicals, in the case of power systems, heat, in everywhere the hydrogen will be utilized now. They are planning to utilize each and everywhere. That's why people are now more concentrating on the hydrogen. So you can see, this will show, so this is, circle. So this is no application towards very low and likely to adopted, and it is the high. In the case of no high, it is very much useful in the case of synthesis of fertilizers like ammonia, and also the cargo ships, and also iron, I know, in the steel industries. So there are many applications, but high are likely adopted is the cargo and fertilizer and steel, like that. So that's why we are telling that hydrogen is a multifunctional. It connects energy, mobility, and industry. Unlike the battery, will be used for only the energy, mobility, and not in industry. But the hydrogen will connect all. So that's why the hydrogen is the magic green fuel in the future. So always the people are talking the green hydrogen. So not hydrogen. They will say that green hydrogen. Why the green hydrogen? There are plenty of colors, no, yellow, pink, purple, like that. Pink means you can get the hydrogen from the nuclear power plant. What is green hydrogen means? It is produced from the electrolysis of water, or you can say the thermochemical with the electricity from the renewable sources like solar and wind or the hydro. But here I'm going to talk more about the electrolysis rather than the thermochemical or any other processes. Why I should talk the hydrogen now? You can see this graph. This is no graph of temperature of the last maybe the 22,000 years of global temperature. You can see from a last glacial maximum, that is 2,000 years ago, the temperature rise is very gradual, and after that the temperature rise was more. That is, but today modern warming has disturbed that stability. So this is not natural variation. It is a human driven. So the rapid spike shown in the graph here, you can see the temperature rises rapidly because of the greenhouse gases. So according to IPCC, the Intergovernmental Panel on Climate Changes warns that without drastic action, we are on the track for plus 2.5 degrees centigrade to 3 degrees centigrade. If the temperature rises, what will happen? So this is the climate risk. So this is no comparison between 1.5 degrees centigrade rise versus 2 degrees centigrade centigrade in the global warming. What will happen? No, extreme weather and species will be affected. Under water availability will be low. People will be suffer, and sea level will be rises. So for a small change, that is 0.5 degrees centigrade rise in the temperature, will affect all over the earth, all over the society. The entire globe will be affected by the temperature rises. These temperature rises may be due to the carbon dioxide emission. You can see the December 2024 425, and December 2025 it is 427. So by the way, you can see temperature rise in 23 and 24, now it is 25. Because of the action we are taking, the temperature rise was going on, decrease from 23 to 25. So normally the natural greenhouse gas effect will not give the climate change. This always give the warm effect to the earth. But the human enhanced greenhouse gas effect only making the system changed. So mostly the people will talk, no, carbon dioxide is the major greenhouse gas, like, but it also the HFCs and PFC, methane and SF6. There are so many other gases other than the CO2 also making or creating the global effect. This we have to understand that not only CO2, carbon dioxide, but also all other gases also making the hydrogen. So this will happen no atmospheric rivers. No, the CO2 and climate change will always make the atmospheric rivers. That means so suddenly within a minute the rainfall will be higher from 1 centimeter to 20 centimeter. So that is called, normally in 2020 or something, in America, they made a pineapple express like that. So these type of things will be because of the climate change. So always know many flood, forest fire, ice melting, sea level rise, everything will be happen. So always we remember that CO2 is a greenhouse gas having the life of 300 years of average. That means our third generation will also affect. So now we are liberating the CO2 means our third generation will be affected. Not only the present generation, second and third generation also affect because of the CO2. For that, they are making the website called Climate Club. So this will show that what will be today. So their target is 2028. So we have only 3 years to 230 days to take the any action. Suppose we are not taking any action, the emission temperature will be rise. Suppose we are taking a small action means definitely there is a change in temperature and the emission, and we are taking the severe action means we are getting low emission and low temperature, our earth will be saved. So you can see, this graph, what will show, global greenhouse gas. So whenever there is a tragedy or something will happen only, the CO2 will be reduced. For example, you can see in COVID-19, almost 7% of CO2 will be reduced from the atmosphere. And also, in the Second World War, the same like 7% of carbon dioxide will be reduced. But our ultimate goal is we have to reduce at least 50% by 2030 to make the temperature rise by the 1.5 degrees centigrade. So our goal is 2050 is the net zero emission, but beyond that, we want the net negative emission. That is our goal. Beyond 2050, 2070, we want the net negative emission rather than the net zero emission. For that, everywhere there is a ranking based on carbon emission, energy transition, and green society, so many things. The ranking is up to 7. Now India is at 4.25. We are only in the middle of the rank. Things to take care to reach the marking of 7. Okay, now no, there are so many oxygen bars are started in Delhi because of the CO2 emission. So I will come to the point that we want the green energy or renewable energy. There are plenty of energy systems are available. So today I am going to talk about the hydrogen energy by the electrolysis. So the hydrogen is not a new one. Everybody we know that it is almost 400 years of history. It was started in 1671. So the iron piece was dissolved hydrochloric acid, and they found out there is a fume, it was highly flammable. So this started in 1971, And the concept of electrolysis, it was in 1800, almost 225 years before. So going on, the this type of hydrogen naming different systems, it was going on, started in 2000. Our target in 2025 to 2050 is the markets and infrastructure continue to for the commercial development. So this is the ultimate goal for the all over the world in 2025 to 2050. This is just like a cartoon. Earlier only the fossil fuel batteries will fight. I am going to be replaced like that. Now it was the hydrogen is going to be the lead, and the fight between fossil fuels and batteries because of the hydrogen. Almost the oil will be buried in soon. So this graph, you can see 1956 it was predicted. The oil age it is going on. So up to 2000, the oil age was peak, and now we are in the hydrogen peak. So it was predicted in 1956 by Habers. So we are consuming fossil fuel about 1,000,000 times more rapidly than the rate at which it was produced. So this graph shows now we are in the hydrogen age. So you can see the solid type of things are going on decreasing, and also the liquid fuels are also going on decreasing, and only the gaseous fuels like methane and hydrogen will be the future. So this graph clearly showing that only gaseous fuels are in the future. Apart from that, the energy point of view also hydrogen in the top. The challenge is renewable means solar means this is only we can get the intermediate. Even the wind also we can get the intermediate. So that means how big we are going to fix capacity. So many things are there. And you can see, scientifically, you can compare the energy density, that is gravimetric energy, that is energy density per mass is more in the case of hydrogen rather than the lithium batteries and all other fuels. That is 150 megajoules per kg of energy is for the hydrogen. And you can see the volumetric energy density, that is energy density per volume. Here, the energy density per volume is low. Everybody know that it occupies plenty of area. That's why we are making the hydrogen into ammonia. So here also the hydrogen in the different form, that is ammonia is the highest volumetric energy. In both cases, gravimetric and volumetric energy density, hydrogen is the future. You can see the production pathways means this is the hydrogen source input, either natural gas or liquid hydrocarbons or coal or biogas, biomass or water. Whatever the case, you can take the hydrogen input, we supply the power. Everywhere the power is required. So the natural gas plus power or biomass plus power, you can get the carbon dioxide. So it need CCS, carbon dioxide capture system. But only the water with the power only, there is no carbon dioxide emission. That's why people are more concentrating electrolysis and thermochemical and solar chemical water splitting. So today I am going to talk more about the electrolysis rather than the other systems. So you can see the gray hydrogen is giving 22 to 26 kg of CO2 per kg of hydrogen. But in the case of green hydrogen, it is almost 0 kg of CO2. So this is the water consumption and cost. Cost wise, now the gray hydrogen is more less, green hydrogen is the more. But because of the solar and wind energy cost, now the cost of green hydrogen energy is going on reducing. So ultimate goal is we have to produce the hydrogen with renewables, either with electricity or without electricity. So the renewable with electricity means you can take the hydropower, wind power, or bio, geothermal, solar, whatever the thing, then you can pass to convert to AC or to DC and send to electrolysis cell, you can get the power. So these are all the different pathways of electricity from the renewable. Another method is production of hydrogen, renewable, but without electricity. Here there is no need of electricity, but you can produce the hydrogen by the renewables. That is called electrochemical photocatalytic, maybe biological photoelectrochemical, solar thermal, or fermentation. This means the chemist or the biologist or the physicist, anybody can produce the hydrogen from the renewable either by the electricity nor by the without electricity. So here it is the timeline for the electrolyzer development. It was started in 1800, and for initially it was a concept. Then there is a 1900. It is a fast development. Now it was the time for the new challenges to develop the electrolyzer for the low cost. So this is the timeline for the electrolyzer development. So these figures, this shows that earlier days in 1776 to 1810, how the hydrogen will be developed. So there are so many histories are available to produce hydrogen in the olden days. You can see the cylindrical pressurized cell. It was 1888 and 1902. There is a big size electrolyzer, and you can see the 5000 ampere electrolyzer developed in 1800, and this is now 135 megawatt alkaline electrolyzer in 1949, and this is a 740 nm cube electrolyzer. There are the alkaline electrolyzer were 100 years old, so they developed earlier the alkaline electrolyzer with many filter price, so many things. You can see Dinora, like that. There are many people concentrated on the alkaline electrolyzer. So if you see the type of electrolyzer, it is called PEM, proton exchange, alkaline electrolyzer, and anion exchange, and solid oxide electrolyzer. Here there is no membrane, only diaphragm, and in both proton exchange and anion exchange, there is a anion exchange membrane and proton exchange membrane. And SOC, this only the high temperature electrolysis. There are so many parameters like only proton will exchange, only hydroxide will exchange. Here only hydroxide will be exchanged. Here there are precious metal. Here there is a non-precious metals, like that they are using. So there are many pros and cons. If you take alkaline electrolyzer, is a mature technology, cheap catalyst, and low capital cost. In the case of PEM, it is higher efficiency, therefore smaller, and it has the work better with fluctuating current, and work better with the high currents. So in the case of anion exchange membrane, this is a mixer of alkaline and the PEM. Here also he doesn't want require iridium, but in the case of PM, we want iridium and the platinum. So there are many pros and cons in the case of this type of low temperature electrolysis. I can say the alkaline electrolyzer is the current king of the electrolyzer technology. Then the proton exchange membrane and anion exchange membrane are the teenage challenger, like that I can say. So now the people are, industries are, the experts are confusing which one is better for India, which one is better for cement industries, which one is better for pharma, which one is better for cement industries, ammonia industry, either AEM or PEM or alkaline. But generally it is a water splitting. So the AEM, you want AEM, or alkaline means you have to handle with KOH or NaOH. AEM means now only in the developing. PEM means you want iridium and precious metal. There is a big confusion. Still it is going on which one is better for the which industries. Whatever the case, you have to know that what you want. If you want to develop the electrolyzer, you have to see this graph. So this is called 1 point. You need minimum of theoretical voltage of 1.25 volt to split the water into hydrogen and oxygen. But it won't be happen because of the cathodic activation over potential, anodic activation over potential, and resistance, everything. So you can expect the hydrogen evolution at the cell voltage is 1.48 volt. That is called thermoneutral voltage. Beyond, so now 2 volt, 1.8, the people are reaching to 1.48 volt to reduce the cost of hydrogen. So this is the common graph one can know before starting the electrolysis. So before starting the electrolysis, you can identify the target reaction, which one you want, oxygen or hydrogen, and choose suitable catalyst material and optimization catalyst composition and the electrocatalyst characterization. There are many steps to achieve the 1.48 volt to generate the hydrogen. So this is the a little bit I'm going for the catalyst. As you said, I can set alkaline and acid. That is called alkaline electrolyzer or AM electrolyzer. Here it is the PM electrolyzer. Here we want the noble metal. Here want the nickel based metal. Here it, the disadvantage is the noble metal like platinum, palladium and iridium. So the solution is either to reduce the noble metal loading at a cathode simpler than at anode because the higher oxygen over potential. So how to reduce the content of platinum or how to replace the platinum in the case of PM electrolyte. That is the concept nowadays going on. So this is the three-step reaction like Walmer and hydroxy and Tafel-Slope. So if you want to see the mechanism behind that, you can go for cyclic voltammetry and linear ship voltammetry like that. Then only you can find out which catalyst is better. So one way we found is how to reduce the platinum is the small system. Here there is a proton exchange membrane. Here you can use the platinum solution plus sulfuric platinum solution. Here is the reducing agent. So you can pass this reducing agent. You can pass the platinum solution. So the platinum will be reduced in this side and deposited on the one side of the membrane. So that you can do trial and error method, which is best. That means which gram is or which gram per centimeter is best for your electrolyzer. This is the one of the method. Another method is to take the support like carbon or graphene or activated carbon like that. So start with 80%, 60%, like that. So there are many supporting metals are there, and you can coat the platinum and find out which supporting material is better. Apart from that, platinum free catalyst like cobalt based, nickel based, like that, many researchers are going on to replace the catalyst. So here is the anode catalyst. So here only I can say that the more over potential or losses will be available. So this is a three-step reaction. We want increased stability and also understanding and tailored design of the OER catalyst. So this is the ultimate goal. Normally, oxide formed on the metal surface always affects the reaction mechanism and electrocatalyst for the OER. Hence, the use of oxide anodes, that the oxide is more stable than the metal. So that's why people are going for iridium oxide, ruthenium oxide, nickel oxide, like that oxide based catalyst will be used. So here oxygen evolution reaction at the oxides. Suppose if you want to go for the acidic medium like PEM, you can select for the rutile type RuO2, IrO2. Or if you go for the alkaline, either in the AEM or alkaline medium, you can go for the perovskite type or the spinel type. So this is the general view. You can select which type of reaction you are going to do for the OER and select the suitable catalyst. The same like, so this is ruthenium based and iridium based, and also this is non-iridium or non-ruthenium based catalyst research is going on. How to reduce the iridium content in the anode catalyst. There are many references are available. So another way is they are making the anode side, instead of oxygen you can make a different reaction, thereby you can reduce the oxygen side over potential. Suppose here it is the OER, you need the highest voltage, that is 1.23 voltage. Suppose if you are going for the ethylene glycol oxidation reaction or ethylene oxidation reaction or iodine oxidation reaction. So you can do this type of reaction in the anode. So the voltage will be less. So that you can produce the electrolyzer or hydrogen at a 0.36 volt rather than the 1.48 volt. So you have to think very sensitively so that you can cross this hill by very easy method. Otherwise, you have to climb and go for this side. So before going to the research, either if you are going to for the OER or you can go for the another method. So thereby you can reduce the energy consumption. As I told, the availability of iridium is very less. And in 2018, South Africa occurred the 87% of the global iridium production. So always if you use iridium, we have to peg the South Africa. So it should not be that means the electrolyzer is not the indigenous one. So you can price is iridium is going on increasing, platinum is also going on increasing. The global annual production of iridium is only 7 to 8 tons, but we want 20 tons. It is not at all possible to use iridium in the future. And this graph shows India doesn't have any precious metals. So that means we have to go for the alternate material rather than platinum and iridium. So this is the development of timeline for the PEM electrolyzer. Now I am going to concentrate on the PEM electrolyzer. The first PEM electrolyzer were developed by General Electric in 1970. And there are many improvement in 2020, kilowatt, megawatt, gigawatt scales are now developing. So this is called the PEM electrolyzer. So there is a membrane, there is a cathode catalyst, anode catalyst, and bipolar plates and gas diffusion layers. So assemble with the end plate, it is called the cell structure of the PEM electrolyzer. So you can assemble one cell, two cell, three cell, it will be the stack. So here is in the anode, oxygen will be evolved. In the cathode, hydrogen will be evolved. Here we can use the Nafion membrane. As I said, platinum as the catalyst, iridium as the catalyst. So this is the general view of the PEM electrolyzer. The major components is bipolar plate, gas diffusion layer, anode catalyst, membrane, and also the similar cathode bipolar plate. So you can see the anode catalyst means iridium. So we have to go for the non-iridium catalyst. Like this cathode catalyst, we have to go for the non-platinum. So there is another challenge is we are now using the Nafion. This is the only monopoly of the DuPont. Now, so all the countries are trying to replace the Nafion with the many cation exchange membranes. Another challenge is the current collectors. So always hydrogen side, you can use the carbon papers or felts. But in the case of oxygen side, you can use only metal because of the carbon corrosion will be takes place and CO2. And now we are using only the titanium plate. Now the challenge with the mechanical engineer or chemical engineer is you have to make a composite bipolar plate to reduce the cathode electrolyzer weight. So that is a challenge in the case of cathode catalyst, anode catalyst, also the current collector. That is the challenges for both engineers and the chemist. And this shows if you see the interior of the electrolyzer, there is a flow field pattern. The chemical engineers know that the flow field is how important in the case of electrolyzer. Both water and gas will go out, how it will affect the system and the energy efficiency. And there are many designs are available. So now what is the research and development activities on the SICRI CSIR in the case of PM electrolyzer? We started in 1995, this type of electrolyzer. Now it is 2025. Last 30 years, we are doing this type of electrolyzer, starting with a small one, and now we are in the very big size. Like I will show the details. So 96 to 2000, we are did a small electrolyzer using the Nafion. Everything was commercial, Nafion, platinum, and iridium. So this is a small design, and this is a prototype model we developed. This is for not for energy. This is for the hydrogenation of oil. First, India given the challenge in 1996 to make the electrolyzer for the hydrogenation of oil. So then we are characterized, we are getting very good results. So based on our knowledge, so we are gone for the little bit higher with our own funding, like 0.4 meter cube, that is 40 liters, like that. And we are done many things to replace current collector, everything. And this is the next version. Finally, in 2000, we developed the 1 nm cube, that is 1000 liters of hydrogen per hour. So you can see this is the entire electrolyzer system, and this is the lighting, and this is the fuel cell. In 2000, we demonstrated that our own electrolyzer, our own fuel cell, we are lighting the entire lighting system. We are this one demonstrated, very big membranes, very big catalyst coating, everything was done. So later we developed 2000 liters and 3000 liters and 4000, 5000 liters of hydrogen per hour. So slowly, it is not very easy to scale up the electrolyzer, because very difficult complement designs are available. So now we are going for 10 or 25. In 2023, we are thinking that we will go or not. But by the way, we got the funding to develop the 25 kilowatt. So at present, this is called 13 kilowatt capacity of electrolyzer. We have the entire system monitoring and everything, balance of plant, everything we have that. You can see that small video. This is the PM based electrolyzer. Here we are electrolyzer operating and hydrogen storage, oxygen storage, and you can find out. You can see the oxygen here, and you can see the hydrogen here. So this will give 6,000 to 7,000 liter of hydrogen per hour. Whenever if you are interested to visit SICRI, you can enjoy this facility and see that how PM electrolyzer is working. So still we are going on working on how to reduce the iridium and platinum by the different methods. You can see big plates are we are developing, and we are compared with the a small size 100 watt to 5 kilowatt to 25 kilowatt. Whatever the increasing for small size to big size, our energy consumption, that is cost, is very same. So after the development, so the industry came, we demonstrated, and we transferred this technology to the Eastern Electrolyzer. Delhi-based company is now the license holder of our own PM electrolyzer. They are going on installing our electrolyzer. This is the one photograph electrolyzer technology installed in Oman. This is the balance of plant. This is the Indian-made electrolyzer operating in the Oman. Now we are going for the solar power, that is fully green energy based things. So the world is given very big target of 2050. Now we are all this the current density, and we have go for this much of current density. Energy wise, they are giving very big target to everyone electrolyzer researchers. So I am happily saying that CSIR-Central technology is very competent to the all over the world. Here, this is the plant. Suppose if you want one very big plant of hydrogen energy, it is not done by single discipline person. We need a chemist to make the catalyst. We want the engineer or electrical engineer or electronic engineering for the control system. We want the mechanical engineering for piping and other things, and we want the electrical engineer for the rectifier. So if you want to develop the complete electrolyzer system, we want chemistry, physics, mechanical and chemical and all type of engineers. So there are many challenges in the case of electrolyzer, in the case of bipolar plate, membrane, catalyst, GDL, PTL. Still there is chances are there to develop the PEM electrolyzer technology. Another one is the alkaline water electrolyzer. Here it is, we are using sodium or potassium hydroxide, but there is no membrane, only the separator. That means here also the 1.23 volt. Only thing, the current density is very, very low because of the resistance of separator and other. So this is the one type of electrolyzer. Now it was started in a preliminary stage. So in 1800, as like PM electrolyzer, now it is a 2020 AM electrolyzer, like that it was started. So in 1900 to 1920, this is called alkaline electrolyzer, filter press type. Now you can see 20 to 25 very advanced version of alkaline electrolyzers are available. There are many methods of preparation of electrocatalyst, but the electrode deposition is the one of the best method to make the catalyst. So I am proudly saying that we made in 2000, I think 2020, only electrode for the alkaline electrolyzer. This technology also transferred to the Eastern electrolyzer for their own technology. Now we are made a 5 kilowatt alkaline electrolyzer, they continuously operating. So you can visit our lab, you can see the alkaline and the PM electrolyzer. Our research is going on, developing the electrocatalyst for the AM and the alkaline electrolyzer. The same like if you want to make the complete system, we want the. So one thing the people will say, earlier I said whether the catalyst is available for the alkaline electrolyzer means yes. So you can see totally we have the 200 nickel consumption and 200 million tons of nickel is available, but we want only 23% of known reserve. So plenty of nickel is available for the alkaline electrolyzer. And always, if you compare alkaline electrolyzer is mature rather than the PEM and SOEC. Energy wise, almost all are same. And long term energy is 42, here 45, and here it is 37 kilowatt hour per the kg. If you take water consumption, comparing with all methods of hydrogen, we want the same like water consumption is required for the hydrogen production. People will say that where is water availability like that, but comparing with all other system, we have the plenty of water. The alkaline anion exchange membrane means you have to develop the anion exchange membrane rather than the cation exchange membrane. Now we are just started a small cell and small membrane and the catalyst. This type of research is going on everywhere, but CSIR also doing the AEM. And next type of electrolyzer we are doing is the seawater electrolysis. Directly you can pass the seawater to electrolyzer, you can generate the hydrogen. There are many systems are available. Only we are concentrating on the forward osmosis electrolyzer. So this is the small type of cell we are using the directly seawater without treatment and making the hydrogen. These are all the advanced electrolyzer systems we are doing in CSIR, very small size cell. And another system is capillary feed electrolysis. Normally you can see in all the electrolyzer, electrolyte will be in the anode and cathode tank. But here is the there is no electrolyte in the tank. Here there is a separate electrolyte tank, but by the gravitation, the electrolyte will be come here, and here there is electrolysis will be takes place. This is, by the way, you can reduce the liquid resistance, you can get the more efficiency. You can see this graph show we are getting very good results of the capillary feed cell than the conventional cell. We are also making the SO2 electrolysis generate hydrogen and sulfuric acid. Many places the SO2 is available. If you utilize, you can get hydrogen and the sulfuric acid. The high temperature, we are not doing the high temperature. It required more than 600 degree centigrade. So this is the technology development timeline. 1977, the basic research studies on electrolyzer are started in SICRI and going on. We are never stopped anywhere this electrolyzer research in 19. There are many achievements are taking place in all 30, 40, 50 years. So ultimately 2020 is the megawatt scale. But as a research laboratory, it is very difficult to go with immediately small size to big size. But we are going on doing last 50 years the electrolyzer research. We are always concentrating on a KPI, that is key performance indicators like energy, lifetime, size, startup time. There are 10 parameters we have to take care for the electrolyzer development. But one thing you can see, there is a trade-off between efficiency, durability, and cost of electrolyzer. So one parameter can usually not be improved without a detrimental effect in the another one, which leads to optimizing design based on the trade-off and application. Suppose if you increase the current density, you can get the production rate more. Membrane thickness increase, efficiency will be more. The gas permeation will be reduced, then purity and lifetime will be more. So the catalyst layer will be reduced, you can get more lifetime. So it is not one parameter will decide the efficiency of the electrolyzer. The same thing from the graph, you can see the efficiency, operating expenditure and the capital expenditure is always depending on the different parameters. And the capex is going on decreasing, and the size of individual electrolysis system is going on increasing. As I said, we want the expertise in fluid mechanics, chemistry, and material science, electronic engineer for the development of electrochemical system. And also we need the more critical minerals, even for the solar panel, even for the electrolyzer. We have to concentrate how to minimize this critical material for the development of even solar panel and the electrolyzer. Now the artificial intelligence came to make easier for the electrocatalyst and stack design. Thereby we can reduce the cost of research using the machine learning and the AI. So we are also going towards the non-noble metal catalyst by the photoelectrochemical method. This is here I want to show that we are making TiO2, SiO2. Here, mechanical engineers, we know that always we can go for the sandblasting for the many purposes. So we want to plan something for the sandblasting. So here we normally use the silica. Here it is a titanium plate. When we are analyzing the surface, we found that there is a formation of TiO2, SiO2 because of the high temperature in the titanium plate. So this will give the very good efficient. So it is very easy method to produce the TiO2, SiO2 by the just sandblasting mechanism. By the way, we are using the alumina as a material, and we made Al2O3 TiO2 like that. And we are also concentrating on iron-based electrocatalysts like ferrite, calcium, cobalt, nickel, ferrite. So to replace or improve the efficiency of nickel-based catalyst. Ultimately, we want to start with the research and development and demonstration and the deployment. Everywhere there is a challenges like capital cost reduction and low cost durable membrane like that. Now there is a new concept called the trillions of tons of underground hydrogen is available. So it will give power to 1,000 years. The research is going on drilling the earth whether the hydrogen is available or not. So this will be maybe it will be generated by the radiolysis or serpentinization or many possibilities are there to produce in the hydrogen in the underground, and you can get drilled and get the white hydrogen from the earth rather than the other electrolyzer. But one can understand that if you want to do the hydrogen research, it will be more careful. There are so many disasters are happening in 1908 to the disaster is going on happening because of the careless. You can see there is a plant damage after the explosion on 30th November 2025. So this is in South America. So we have to be more careful on the hydrogen research. Whenever you operate the big sites, we have the more sensors and careful operating systems will be available. In the case of hydrogen storage, there are many methods are available, either in the chemical based or material based or physical based storage. But we are not doing any storage. That's just for the knowledge shake I am giving. And you can store either in the gaseous state or liquid state or solid state. TRL is more in the case of gaseous state, and also the liquid state also 7 to 9. Whatever the storage is suitable, you can make use. And you can see hydrogen stored in cavern means you can make store up to 1 year. Even 1 terawatt hour of hydrogen may be stored comparing with the other things. And just I can go for the pioneering perspective of the green hydrogen. So India's hydrogen target is 5 metric ton per year. So this is ultimate goal. The different countries are different goals. So this is the comprehensive utilization. As I said earlier, there are many places. As Swiss knife, it was used for fuel application and transport. Many application it will be used. So you can see, Bharat Benz and Reliance developed a bus for the 400 kilometer, and the hydrogen-based fuel cell bus trial begins in Pune. That is October 25, and Maharashtra Energy and Pune based company and Indian Oil Corporation made one electrolyzer and bus. It was in trial, and this is in South Korea already started in commercial application, car and buses. Here it is the China hydrogen energy urban train. You can see the novelty is they are in the fuel cell the hydrogen will be generated. The hydrogen will be purified and recycled, which is then used for the washing and heating and cooling in the carriages. So they are generating the hydrogen, utilizing it as in fuel cell, and again the water will be used for the many areas. So this is the aviation. Now we are talking about hydrogen is used for the aviation, but it was started in 1783 with air balloon. It is going on developing, and ultimately in 2040 is the 200 seats like that. And Berlin airport is planning for the complete hydrogen, no coal based or nuclear based energy, only the hydrogen based electrolyzer you can generate and store and utilize. That is the ultimate goal. So in future our houses are also hydrogen based houses. We can generate the solar panel, hydrogen and fuel cell. So the home energy storage system market is expected to grow at a 33.7% of CAGR to reach almost double in the case of 2031. That means our houses are completely greenhouse in 2031. In many places, our hydrogen will be used in Paris towers and also the flight engines. So you can cost-wise, you can see in 2020, the cost is very high, around 7 euros per kg. In 2030, little bit low, around 4 euros per kg. And in 2030, it was 40, it was less, and 2050 almost all over the world the cost will be around €1 per kg or $1 per kg. So this is the example that how the cost will be, uh, uh, cost of hydrogen used in many places. You can see this is the present fossil fuel based cost. Suppose if you are using the hydrogen at a cost of $2 per kg, so the change is more. That is, you have to pay the more amount. Suppose if you get the hydrogen at a 0.5 cents per kg, you can get the cost reduction. That means you can see, in the case of fertilizer production, there is going for the minus 15% of cost reduction. That means we have to produce the hydrogen either almost $1 per kg or $0.5 per kg. Then only the cost will be less rather than the present situation. And ultimately, you can take steel and shipping and fertilizer industry. The final impact on the end product cost is very, very low. So maybe it will be higher in the case of intermediate product, but in the finally the cost variation is very, very less if we use the hydrogen systems in the fertilizer and the shipping and the steel. So this is the confidence in role of hydrogen and the readiness level. The confidence is more in the aviation, shipping and steel, but readiness and confidence is in the case of fertilizer and refining and methanol. So in the case of confidence level is less in the case of gas grid like that, and readiness level also low. So these are the same thing I am giving the different way that industry, transport, energy. Only in 2050 the complete system will be high. That is complete confidence level and complete TR level only happened in 2050 or the 2045. This is, for example, you can take the ammonia industries. You know that the Haber process, the hydrogen will be reduced in natural gas, and we have to spend more. We have to no compromise that this type of CO2, that is 1.22 ton of CO2 will be generated 1 ton of ammonia. So that's why we have to replace complete the Haber system to the electrolyzer base. That means you can hydrogen generation here only 0.35 to 0.49 tons of CO2 per ton of ammonia. That is, you can generate the hydrogen from the either AEM or PM like that from the solar panel, and nitrogen from the air. You can just pause for the hydrogen system, so that you can eliminate this type of CO2 emission. You can see we want 12 billions kilogram of that means this much kg need 240 billion kg of hydrogen. So only electrolyzer is possible to generate this much of kg of hydrogen. No other systems are possible to generate this much of hydrogen to make the ammonia industry. The same like steel industry, if you take iron ore of 1.6 ton, it will generate 1.9 ton of CO2. That means we are getting more CO2 than the more ton. That means more CO2 in the blast furnace and also from the coke and coal. So that's why we are going for the direct deposition or the method like hydrogen process. Here, the chemically reducing the iron by using the hydrogen, then you can get water rather than the CO2, and finally you can get the crude steel. Same like hydrogen per ton, roughly we want 19 kg of hydrogen per ton of steel. That is equivalent to 3 megawatt hour of hydrogen energy. That means India's 2030 target is aiming for the 15 to 20 million tons of green steel production. That means you can assume that how much hydrogen is required. That means this is the conventional process, you can get CO2, and this is the modern process, you can get the water rather than the CO2. Okay. And this is the challenge in cement industry. We are going on replacing the existing cement manufacturing system to the hybrid electrolyzer system. Again, India's cement production is more. This is I am telling that hydrogen in the case of ammonia, but cement industry also required the more hydrogen. So here you can see the industry specific opportunities. We want the hydrogen in the case of refining, chemicals, and iron and steel. So you can go for natural gas to either green hydrogen or pink hydrogen or the blue hydrogen. Here the hydrogen from the coal or carbon. So everywhere either you can go from the coal or natural gas to blue or green or a pink hydrogen. So this is the ultimate goal for the hydrogen system. And now there are in India, there are many places hydrogen valleys are going on. So to installing the energy source, and you can produce and you can store and you can transport and you can also use for synthesis or for the vehicle. So this is called the hydrogen valley near Cochin Valley, Pune Valley, in Andhra, Amaravati Valley. There are so many places government is funding for the hydrogen valley for India. So this is in 21,600 kg capacity of hydrogen bunk was put it in the Silicon Valley of America, and in Australia also many places it was started. What is the hydrogen energy in India? That is called Viksit Bharat 2047. Our goal is 5 million metric tons of annual production by 2030. So it will create 6 lakh jobs and a reduction of 50 mmT of CO2 and save 1 lakh crore in fossil fuel imports. So ultimately, this is a goal for India hydrogen energy. They are given, government is given almost 18,000 crores of money for research and the pilot plant. So many things it is going on. You can see that many places India has started 15 fuel cell vehicles and 9 hydrogen fuel station, and this is the ultimate goal for Indian hydrogen economy. So already many Indian industries are started. L&T, Reliance is a huge amount of investment, and IOCL, Chennai Petroleum Corporation, and many private and PSUs are spending the money like anything in the case of hydrogen energy, and there are many MOUs are also going on. So you can see the projected hydrogen demand. You can take that a compound annual growth rate of the many applications like ammonia, refinery, fuel cell, building. In all the cases, the CAGR was going on increases. So there is a 8.32% increase in 2040. You can take ammonia, wherever the application, the compound annual growth rate was going on increasing in India, in all over the world. So one thing we want is it is not electrolyzer development. We also go for the renewable energy. That is, as in October 31st, 2025, India's renewable energy capacity was 259.99 gigawatt. So India has a green hydrogen production target of 5 MTPA by 2030, for which the renewable energy capacity required is 125 gigawatt. So that means we have the plenty of green energy to produce 5 MTPA in 2030. This is the great achievement. The Indian government was installed the gigawatt of green energy in India. So water-wise, the raw water demand, suppose if you want to make the electrolyzer, if you want to take groundwater, it required 12.6 liters. And if it is a treated water, 13.5 liter. If you want to take the hydrogen of 1 kg, you need the 29.7 liter. So if you take all these, you can go for the different treatment processes and you can get the 1 kg of hydrogen. So the according to Indian scenario, we have the plenty of water for the electrolyzer. So water demand for 5 MTPA hydrogen demand by 2030, we have the minimum water consumption is only 0.04 to 0.04 BCM. So we have the plenty of water to make the hydrogen in India. So the Uttar Pradesh and Gujarat are expected to be the key hydrogen consuming states. And the presence of current upcoming refineries and ammonia, urea in Uttar Pradesh and Gujarat is more, and strong chemical belt in Gujarat potentially consuming the hydrogen as a feedstock. That's why the both Gujarat and UP have the cost wise. No, you know that Niti Ayog. So Niti Ayog want the cost of hydrogen at least $1.4 per kg. Now we are here in 2.03, 2.3, but Indian Niti Ayog want 1.4 or less cost for the cost. And this is my price impact on the green hydrogen emission petroleum product. So people will say that the cost of vehicle will be less, but it is not like that. So it is always for at 50% of green hydrogen is mandate. You can assume the price of petrol may rise from 100 to 102. It is not because of hydrogen, the petrol price will not high. And like that, the transport, you can, based on the volume, the cost will be changed in the either in the pipeline or the road. So you can see, Gujarat, West Bengal, now Andhra Pradesh, Maharashtra, all you can see the seashore only getting the importance in the case of hydrogen. Because in the seashore, you can get the oxygen will be used for steel making, and water will be wastewater treatment and water treatment, and you can make use seawater for the desalination. So always this type of sea-based electrolyzer is always good for the many things. And you can know shipping minister is made VOC port. Our Tamil Nadu built a cost of rupees 3.87 crore. The 10 nm cube per hour pilot facility will generate green hydrogen. It is happy that our VOC port also making hydrogen of 3.87 crores. So according to Indian Railways, the Indian Railways has planned to introduce 35 hydrogen trains under the hydrogen for the heritage. Comparing with the global scenarios, Siemens in CRC in Italy, our train power output is 1200 rather than the international world. So our capabilities to run the train is it was comparing with other countries, it was more. Very soon we are going to run a train. So comparing with CO2 emission wise, you can see the diesel train, electrified train, battery train, and hydrogen. The CO2 is very, very less in the case of hydrogen train rather than the battery, electrified, and the diesel train. So that's why the ultimate goal is the hydrogen based trains. You can compare either capital cost or whatever the thing comparison. The hydrogen based trains are cheap and environmentally friendly. There are so many challenges and opportunities in India. So many places the hydrogen based fueling stations are started, and CSIR-Central and NCL Pune developed and demonstrated the hydrogen based car and bus. The NTPC launches green hydrogen buses in Leh, India in 2024, and this is the history made. That is India's first hydrogen bus serving launched in Ladakh by our Prime Minister. So this type of hydrogen utilization is going on happening in the India. So the work on South India's first hydrogen fuel cell station near Kochi Airport is going on, almost going to finish. So the hydrogen buses and cars will load the hydrogen instead of the petrol. And this is Tuticorin is going to install very big hydrogen. That is almost 1,40,000 crores of investment will be going to put in the Tuticorin airport. So many initiatives are started in refineries, petrochemical, ammonia and fertilizer, iron and steel, mobility and transportation, power utility, and miscellaneous many places. There are plenty of ammonia, no hydrogen utilization will be used. If you take the eye view, the hydrogen is used for semiconductor, glass manufacturing, cement, food, electronics, pharmaceuticals, methanol, and backup power, grid energy, aerospace, fuel cell vehicles, gas blending, and hydrogen powered drones and aircraft. So, if you take all these applications, we know only electrolyzer will be served. So that's why the more funding was given to the research-based hydrogen systems in all over the India. Almost many CSIR labs are utilizing the hydrogen and generating the hydrogen based systems. You can see the state-wise hydrogen production. Tamil Nadu is very less, but as I said, Gujarat and Odisha is the maximum hydrogen production capacity rather than the Haryana and also the Tamil Nadu. And if you see that announced is so much and we have very less, we are low active even though hydrogen research is going on. So the most initiatives aimed at advancing clean hydrogen in the developing countries, wherever the hydrogen based thought or meetings or research, India will be placed. So the developing countries means comparing with all other countries, India is doing many R&D things, and there are regional alliances and initiatives. There are 6 regional clean hydrogen initiatives. In Asia Pacific Green Hydrogen Alliances, India is one of the member with all other countries. You can see, we want almost 500 million tons of hydrogen for the different applications like shipping, aviation, road, and industries. So 2050, we want almost 500 to 600 million tons of hydrogen for the different applications. India's green hydrogen revolution is 13 project and spending 7.33 lakh crores of money for the hydrogen research. You can see, in America, different private industries, atmospheric alkaline, pressurized PM, SOEC. This is the American. You can see the Europe. Many industries are already started implementing, doing the research. And comparing with America and Europe, China is a very biggest electrolyzer market. You can see, comparing with all other countries, China is a leading in the hydrogen research. You can see the Asia, maybe Adani, Eastern Electrolyzer, only the maybe 10 to less than 10 industries and PSUs are going on the hydrogen research. So water will be the fuel of the future. So this is the statement given in 1875. Water will one day be employed as fuel. That hydrogen and oxygen, which constitute it, used singly or together, that is in fuel cell or IC engine, I can say, will furnish an inexhaustible source of heat and light of an intensity of which coal is not capable. In 1875, Jules Verne is given this statement. So water is the core of the present 2025. You can see the coal having the carbon. So we are from coal to oil to gas to hydrogen, zero carbon based energy systems we are now. And we can see the environmental point of view. Hydrogen also the warming effect. So hydrogen is a leak-prone gas that leads to potent climate warming in the near term. Apart from that, CO2 and all other gases, hydrogen also giving the warming effect if in the case of leak will be happen. Because of the formation of methane and ozone and water vapor, everything will also make the climate change or the warming effect. So the crossing the valley of death from the fundamental to applied research or technology is very difficult. So if you do academic research is different, industrial research is different. So you have to cross this valley of death, then only you can go from the academic to industrial research. So every problem has a solution. Now, what is the solution for this? The same situation for also in the case of electrolyzer. If you go one way, it will affect. If you go another way, something will affect. So this picture exactly shows that our electrolyzer research. So one thing I want to say to all, this battery powered bell has been ringing non-stop for over 180 years. It is believed to have almost 10 billion times it was rang. So we don't know something about its basic composition. Through it is a dry pill battery. So we don't know what is the inside the battery it is running 180 years. So we want the Indian technology is like that. So once the technology is developed, no one should bother about this technology. So we want the technology like this. So ultimately, this graph, no, you can see the here there are different colors. This is baseline. This is if you are not doing any research on hydrogen or whatever the thing. If you are going for the net zero, and this color shows the government implications like that. So if you see the I can say that the baseline you can take total carbon. I can say that our global warming take 2100. If you want not doing anything, the rise in temperature will be 3.5 degrees centigrade. If you go for something you can do, it was temperature less. So this region it is called net zero region. If you go for the net zero region, the rise is 1.5 degrees centigrade. So this is a graph showing that the fossil fuel in 2060 and carbon emission in 2060 and clean energy in 2060. Whether if you are going for the net zero or if you are not going for anything else. So if you are not going for anything, the carbon emission will be more. You can see, oil peak here. Suppose if you are not doing 2035 is the oil peak. Still, we are going on use the oil and it will generate the CO2. Suppose if you going for the net zero or doing something at the in 2025 itself, we can stop the oil age. So if you this is the very good fantastic graph showing that what is going to be happening in 2100. So the vision to velocity. So that's why I'm given in the initial stage. That is execution will market the most. Assessing clear responsibilities and ensuring accountability and solving the problems quickly. So if three things are there, so that then only the vision to velocity will be happen. So the electrochemistry, the people and planet centric. So carry the torch for a sustainable future. So this is our entire people, and this is Sikri. Thank you very much for your patience. Thank you very much.
Thank you, sir. Thank you for your deep insights into hydrogen production technologies, future career aspects, and R&D directions. Thank you so much, sir. Let me now invite Dr. D. Periyar, Associate Professor, Department of EEE, to propose the vote of thanks.
Thank you, ma'am.
Any question? Audience or participants, any questions? Dear participants, if you have any queries, you can post in the chat box.
I think no doubt.
It's it is my privilege to propose vote of thanks to Day 2 Session 3. We extend our heartfelt gratitude to Dr. S. Vasudevan, CSIR, CERA, for delivering an inspiring and insightful session. His thought provoking talk, rich with practical knowledge and real world relevance, greatly enhanced to learning experience of all participants. Enhance the learning experience for all participants. The clarity, depth, and passion he brought to the session made it truly memorable. We sincerely thanks to him for sparing his valuable time and for sharing his experience so generously with us. We also express sincere appreciation to the all participants for the active involvement and support which contribute the success of this session. Once again, thank you all for making this session meaningful and impactful. Thank you, sir. Thank you for your valuable session, sir.
All the
All the
participants,
participants,
please
please kindly switch on your camera for the photo session.
Professor, kindly turn on your camera, sir. We need to take screenshot.
Madam, host has disabled ன்னு வருது மேடம் கேமரா கொஞ்சம் பாருங்க. Host has disabled camera it says.
Now it is enabled, sir. Please, all the participants, switch on your
Kindly turn
camera
on
for
your
the
camera.
photo.
Check a minute. Thank you, sir. Thank you for your valuable presentation. Dear participants, please stay online. Our next resource person will be joining us shortly. You can turn off your cameras.
Madam, good evening.
Good evening.
Yeah, so shall we start now? Already I joined this program, right?
Okay, sir. Just a minute.
Good evening to all. It's my privilege to invite Dr. C. Kalaimani, coordinator of this FEP, to introduce next session resource person, Dr. Boopathi. Please, ma'am.
Good evening, one and all present here. It's my privilege to introduce our resource person for the session 4, Dr. K. Boopathi, who has over 23 years of professional experience in the field of renewable energy with strong expertise in wind and solar resource assessment, wind farm planning, site selection, data analysis, turbine performance, DPR preparation, offshore wind development, and project consultancy. He holds a PhD degree in wind farm optimization through repowering and solar integration. He earned his BE in mechanical engineering and MTech in energy engineering and is currently pursuing MBA. He began his career as a faculty member at VIT Vellore, worked on renewable energy projects including solar and biomass systems. In 2003, he joined National Institute of Wind Energy as a scientist, where he played a key role in wind resource assessment across India and contributed to wind data monitoring, site studies, turbine testing, and consultancy services. He later served as a head of wind resource assessment, providing consultancy to government, public sector, and private organizations. His research interest includes offshore wind measurement, wind forecasting, turbine weight studies. He led the wind power forecasting project in Tamil Nadu and contributed to development of national wind potential maps. Currently, he is heading wind turbine testing division at NIWE, overseas research, data analytics, and forecasting activities. He has also contributed to national wind and hybrid energy policies, has trained professionals across the academia and industry. Sir, we welcome you, sir. Kindly take over the session. Thank you, sir. Unmute பண்ணுங்க.
Hello?
Yes, sir.
Can you hear me, ma'am?
Yes, sir. You're audible, sir.
It's gone. I don't know where it's gone. One moment. Yeah, I hope you are in a position to hear, right? Yeah. Just a minute. I'll just share my presentation, then we'll talk.
Sure.
Sharing.
That's fine.
Uh, Ma'am, whether my screen is visible?
Yes, sir.
Okay,
Yours is
perfect.
visible, sir.
Yeah,
Yes.
thank you.
Thank you.
Thank you. Good evening to all. So, I would like to express my sincere gratitude to Madam Kalaivani, Dr. Kalaivani ma'am. So, he requested me to give lectures on emerging trends in digital twin for wind turbine technology. So, it's given me great pleasure to be here today to give lecture on this topic of wind energy and as well as the digital twin for wind turbine and how we are going to generate hydrogen from the green energy resources. So that is my topic. Yeah, so and also I would like to express my sincere thanks to Madam for giving me the wonderful introduction about me. So let me start now. So my topic is digital twin technology for wind energy system. I hope in the previous lectures also you have heard many things regarding hydrogen production, how to under storage and other topic also others might have covered. So let it be there. So now I'm going to give the complete wind energy. So many of them might have heard my lectures previously, the various other program also the wind energy. Anyhow, let it be there. So I'm not going to give the complete wind energy. So I'll give the part of the wind energy. Then I'll go for digital twin. So this is my topic for today's meeting. Yeah. So Madam has given already my introduction. Yeah. Yeah, this is my course overview. So, wind energy focus learning objective. Today, we are going to have a discussion about the wind energy fundamentals, the various things, what it is there, because we have to know how we are going to do the digital twin. So, without knowing this one, we cannot directly go for digital twin. And also the wind turbine, various components and the control system and the performance optimization, and we will discuss about the digital twin technology for wind turbine and how the wind turbine is going to help the production of the hydrogen, and what are the different A and ML techniques for wind power forecasting, predictive maintenance, which is required for the digital twin. So that is my major topic I'm going to cover. So already you know that so energy and sustainability building a green energy greener tomorrow. Right, ma'am. So energy, you know that how we are getting it. So most of the energy currently we are getting from thermal power stations, right? So fossil fuels. So whenever you are burning the fossil fuels, you know the various issues we are facing it. Currently, we are facing it. But anyhow, currently in India has already reached almost more than 40% of renewable energy resources. Right. So, what are the major impacts in the conventional energy resources? Because you know that mostly when you are burning fossil fuel, which emits obnoxious gases to the atmosphere, so that we are getting, the global warming and the climate change effect, it is there. And also because of, when you're burning fossil fuels, it may emit pollutants like particulate matter, nitrous oxide, sulfur dioxide from coal plant, and also have the respiratory illness and premature death is also is happening there. And the World Health Organization, which estimates 4.2 million premature deaths are annually happened because of this outdoor air pollution. So currently, you may know the situation, right? In Delhi, how many of them you have heard in Delhi? So they are not in a position to even breathe also, because of the reason is that the air pollution, still the air pollution, because and as well as the fog is there, they are not in a position to inhale it. So this should not happen. But in India, in Tamil Nadu, we do not have much issues, even in Chennai also. But some other states, like, because in Tamil Nadu, and particularly in Chennai, nearby we have sea, so all the carbon emission which goes to go and sink in the sea surface itself. Right. Other environmental impacts, that mining and drilling, when you want to have fossil fuels like coal, then diesel petroleum products, then you have to drill it, right? So when you are drilling it, then always it's destroy the habitats and the contaminants of the water resource. Now you may also know that just how many of them reading the newspaper, that I do not know that. So recently the many news came for the NLC site, right? Then in and around the NLC site, whenever they want to go for new sites for getting coal, they're always the nearby the villagers, they are protesting, because they also say that because since they are doing the mining, the water is getting contaminated, right? So these are the issues always it's happening there. And also the geopolitical risk issues. So the geopolitical issues, why currently Russia and other countries, they are having fight. Even the Ukraine also, they are having the fight, because of mostly the import reliance. So one country, the Europe is depends relies on other countries fossil fuel, like the crude oil, makes countries vulnerable to price shocks and supply disruptions always there. So that's why they are making one country to other countries nowadays currently. And even though we are taking fossil fuel from in the petroleum product from the sea surface and other surface, still we are depending on other countries for importing fossil fuels. So how you can reduce it, right? So all the other issues also, the climate change impact also will happen because of the rising temperature and extreme weather condition. It's happening there. Some days you may get a drought, other places you may get heavy cold, and other times you'll get the heavy rain. And also because of this climate change, the habitats are shifting from one place to other place. And that the sea levels are getting rises for another 2050, and some other time it may rise for 1.5 degree to centigrade. Then due to that, and also 1 to 1.5 meter also sea level also will rise. And also that ocean acidification is also happening there. And food supply impacts, food supply impacts also is happening there, because of I told you the drought, some places it's happening there. And because of the drought, the animals will shift from one place to other place. Even human beings also may shift from one place to other place. And many health effects also is happening there. The ultimate thing is that the we have to have, sorry, some other things are there. So the need for sustainable energy, right? The sustainable energy is, it is a growing demand. The sustainable energy. So already we have been discussing about wind, solar, hydro plant, and other geothermal energy. So these are the growing demand because currently our consumption of per capita consumption is nearly 1,300 kilowatt hour. But the previously it was 800 to 900. But other country, when you are seeing there, other country like Canada and America, so they have nearly 13,000 to 14,000 kilowatt hour. But still, even though our countries still it's growing, our energy demand is continuously getting increased. That's why and the climate change mitigation. And just now we have discussed about the climate change mitigation. So climate change mitigation, we need sustainable energy like wind, solar, and other system. And also the renewable energy will give the improved sustainability. So sustainability definitely in future also this will not go up and definitely will get the energy again and again. And also health and environmental benefits will get it because there is no gases emissions and carbon emission from the renewable energy resources. So definitely we'll get the health and environmental benefits, right? And also the expanding energy access we can get. Okay, fine. So then National Stop Wind Energy. So I don't know why this, madam. I mean, the blue color line is your system.
No, sir.
Just
No, sir.
it is from my system.
Yes, sir.
Just a minute, because I have never done it. Eraser also not working. I don't know. But all slides are coming. I don't know why. Just a
1
minute.
second,
But
sir.
it's,
We have to
yeah, it is
verify.
not my system. It is not my system. Just
Okay,
check
sir.
it. Because the first two slides it was not coming, but now I am getting it.
1 second, sir.
Yeah. Okay, fine. So Indian renewable energy potential. So you may know that the National Institute of Wind Energy has already estimated the potential at a different heights because the wind characteristics increase with the height, right? At a 50-meter level, we estimated the potential 2010 49,000 megawatt. At 80-meter level, just look at here, it is 102 gigawatt. Sorry, 103. Yeah. So 103 gigawatt and 100 meter 302 gigawatt, 120 meter 696 gigawatt, and 150 meter we estimated 1164 gigawatt. Just imagine it how much is the potential we have in the wind power, and also the solar power also estimated by this National Institute of Solar Energy and as well as the National Institute of Wind Energy together. We estimated 748 gigawatt based on various assumptions. So still we have sufficient power there, and also the biomass we estimated 50,000 megawatt, like the small hydro, and ocean thermal energy conversion, geothermal we have it, and tidal and wave. So these are the these are the renewable energy. It's possible, but already the solar wind we have already captured many captured resources and developed the system for getting meeting our demand, right? So this is the global energy crisis that the climate change what I have explained to you. The challenge what currently we are facing is that global energy demand projected to increase by 50% by 2050. Just think about 50% by 2050, while carbon dioxide emission must drop 45% to limit global warming to 1.5 degrees centigrade. Right. So this is the critical climate impact. So critical climate impact is that rising temperature which affect entire ecosystem, and also this gives the extreme weather events causing economic losses. And the one solution is only the renewable solutions. So the renewable energy which gives protecting environment, yes, of course, the climate protection which eliminates the greenhouse gas emission, and also the resource conservation requires no water for operation, like thermal power plant. That thermal power plant we need the cooling water which requires we are taking from sea surface, and do the cooling water requirement, and also the preserve finite fossil fuel resources, right? And also the air quality, zero emissions of pollutants from renewable energy. So these are all that this is the India's net zero vision. Right. So India has already signed an agreement, the Paris Climate Change Agreement. Government signed because the government wants to go for net zero carbon emission by 2070. But all other countries have already signed for up to 2050. They want to go for net zero emission. And the government of India has also committed to reach 500 gigawatt by 2030 from the renewable energy resources, and 45% production emission intensity of GDP by 2030, and also 1 billion ton of cumulative emission reduction by 2030. You see the 2030 and 2050 and 2070. So 2030, the next is 2070, right? And for national hydrogen missions, so launched August 15, 2021. So they have also many things there in the hydrogen mission also there. I will just explain to you later slide. So Indian renewable energy commitment, so 500 gigawatt by 2030. So already the wind energy has been installed 54 gigawatt. Solar energy has already been installed 120 gigawatt. So we have already crossed 200 gigawatt from renewable energy resources and net zero by 2070, right? Sometimes it's repeating. So the way forward, the wind energy integration, right? So implementation priorities, accelerate offshore. How you are going to implement this, energy requirements. So we have to go for accelerate offshore wind development. So wind development, so we have already more than 7,600 kilometer coastline. So mostly the offshore wind potential location already we, explored. The possibility of explore is only Gujarat coast and as well as the Tamil Nadu coast. These are the two locations. They have good amount of offshore potential. It is possible to install the wind turbine and get energy from the wind farm, and also the enhanced grid infrastructure for renewable integration. But still, so many of them know that the still what we are facing is that we have the resource, enough amount of resource, but we need the grid infrastructure. But government of India has already taken necessary steps to make the grid infrastructure for evacuating the power and repower aging. So the repowering, the initially, the government, at the time in the 1990s, 95s, 98. So those time only the available wind turbine was only, 200 kilowatt, mostly 200 kilowatt, 55 kilowatt, 200 kilowatt wind turbine, mostly which are occupying the high wind potential region. So now we have to replace those wind turbine with the latest technology turbine. The latest technology has, enormously grown, right? So we want to replace that old turbine with the new turbine. The government of India has already, made policy for that. And the next thing is the green hydrogen production. So government of India, they want to go for, the 2021 itself. It has created. Now it's moving. It's a good way for green hydrogen productions, right? And this is the total power installed capacity. Currently, more than 500 gigawatt has been installed in our country. And out of 500 gigawatt, this is India is the world third largest energy production as well as the third largest energy consumption also. And so the out of 500 gigawatt, coal 217 gigawatt. That's the 44% only we are getting from the coal. And renewable energy, we are having, more than, 200 gigawatt we crossed, but little old, maybe the 3-4 months maybe old. So that is a 39% we are getting from the renewable energy resources, and lignite and all others, diesel 589 megawatt, and nuclear, 8,780 megawatt. And hydro already we crossed, large hydro, 50 gigawatts already we crossed. So these are the energy which is contributing, right? This is the total power installed capacity, more than 500 gigawatt, particularly for the wind. So wind has been distributed majorly for seven states, maybe some other state, the 8 states, and the major states are Gujarat and Tamil Nadu only. So Gujarat has already installed 13,000 megawatt. Just look at here. I'm not showing on this. Yeah, so this is Gujarat. So Gujarat already has installed 26%, 13,816 megawatt. Tamil Nadu has reached 11,830 megawatt. previously Tamil Nadu was the number 1 installation capacity of wind, and Gujarat was number 2. So already they crossed us because of the availability of land and other infrastructure. So the Gujarat currently is leading, and others like Karnataka, Maharashtra, Rajasthan, Andhra Pradesh, Madhya Pradesh. So these are the state we have good amount of wind potential, and Kerala has good potential. But the issue is that mostly the winds are the lands are available for development is on the hill station only. But the hill station, the logistic issues are there. So logistic issues are there. Cannot install turbine like the normal land, flat terrains. So this is the energy resources already. I told you what the resource which is available. So this is the energy resource. So India is having the vast potential of wind and solar, biomass and hydropower. Already, these are the energy resources which is meeting our demand. So which is meeting because already, the wind has contributed more than 54 gigawatt, solar contributed 120 gigawatt, biomass already contributed more than 10 gigawatt, hydropower, large hydropower more than 50 gigawatts. It's contributing, and other resources are, under development to contribute like geothermal. The government has already, they want to make one more department for geothermal energy, which is available in the northern Himalayan ranges. Right in the Leh Ladakh region, so they have a geothermal. So I have visited, 3-4 times wherever I had seen. So many places I could see. I've never seen the stream which comes out from the ground, but most of the places, hot waters. Many places I could see their hot water coming out from the hills. So it means that they have good potential there. So definitely we are also going to explore the possibility of geothermal energy, and tidal and others. It may come later, not currently. Tidal and wave energy. Right. So this is the wind potential map what I have informed. So this is the 50-meter potential. We estimated 50-meter height. We estimated 49 gigawatts. Say 80-meter. This both we prepared in 2010. And since the turbine capacity is getting increased, and the hub height also has been increasing, then we want to estimate the potential. Also depends on the hub height. So in 2015, we prepared the map and we estimated 302 gigawatt, and 120, 2000, maybe the 20 ranges. The 15 is the 20. We prepared the atlas for 120 meter. We estimated 696 gigawatt, 95 gigawatt. And recently in 2023, we prepared other map. So the other map, the 150-meter level, which shows 1165 gigawatt. So this is the potential. Now just look at here. These are the western coast, coast and western Ghats side only. We have good amount of potential because we get the strong wind from southwest. Right. So this is the 120-meter and 150-meter potential. The red color region shows the highest potential region, and next to the orange color, next, because you can see here red color, which is having the greater than 40% of the capacity utilization factor. And the next, the orange color is having the 38 to 40%. Like this, just you can see the color code. So the color code which indicates what is the potential of this particular region. So this also which is available in our website. If you want to, just you can go to our website. You can go to our website and just click the map, 120 and 150-meter level map. You click any location which gives information about what is the location and what is the wind speed range, what is the wind power density range, and what is the capacity utilization factor. So all these things just you can get it from there. So here what it says that capacity utilization factor in terms of percentage. What is the actual generation possible? What is the actual generation it can, it's generated by the turbine. What is the maximum possible energy generation can be generated by the turbine. So this is called the capacity utilization factor, CUF. So generally for the fossil fuel, we say that the plant load factor. But here we say the capacity utilization factor, right? So this is the capacity utilization factor is the percentage. Okay, fine. And also just we estimated the solar radiation resource assessment also. The solar radiation resource assessment, what it says that the global horizontal irradiation. So this irradiation which gives, it's a moderate amount of solar energy for generating electricity from the solar PV. But the DNA direct normal irradiation, what it shows that it shows a very poor quality, even though we have good amount of sun, the DNA normal irradiation is very low compared to GHI. So this is, these are the map, right? So this energy resources, the natural gas, oil, coal, and nuclear, is the non-sustainable. This is the sustainable energy, that wood, biofuel, solar, hydroelectric, geothermal, and wind. And what this map which indicates that the highest potential is in Rajasthan. So Rajasthan, we estimated the potential is 284 gigawatt because the area is vast and the wind density is little low because in this region is a desert region. Since the temperature is always higher than this region which has low density of wind. And you can see the Gujarat. Next, if you come to the Gujarat, the next potential we have Gujarat. Yeah, Gujarat is 180 gigawatt. 180 gigawatt we have it. Andhra Pradesh 123 gigawatt. Maharashtra 173 gigawatt. And Tamil Nadu, we have only 54 gigawatt, right? Yeah, 95 gigawatt from the Tamil Nadu. So these are the state having good potential. Yeah, Karnataka already 169 gigawatt potential it is there. So these are the major states which is contributing, and you can also see other states has not yet been explored. Maybe if we go to the higher height of 150 meter, we may try to get explore other states also. So this is the potential. Then just what I want to say here is the wind energy. So energy always we need energy can neither be created nor can destroyed, but can change from one form to another form. Just I'll give some basics of wind energy. Yeah, so the wind, wind is nothing but the motion of air related to the Earth's surface. It can change it from one place to other place. Right. So it is a variable in resource. It is not continuous resource like, for example, thermal power station. If you want to generate electricity from thermal power station, your demand is, for example, 10 megawatt. Your demand is 10 megawatt. Demand is 10 megawatt. Suppose we want to generate electricity for 10 megawatt continuously, then if we have the coal resources, that is coal, you can continuously pour coal and generate a steam. You can the generator steam by using the turbine, it can generate continuously 10 megawatt. But here the resource of wind is it's a variable resource, right? It means that it will vary from place, every place, just the wind will vary, and also every second also the time to time will vary the wind, and also the place to place also will vary the wind. So that is the nature of the wind. And also the wind, it will not a continuous one, and also season to season also will vary. For example, in windy season in Tamil Nadu, and mostly the southwest wind will start from May to September. So this is the southwest. Currently we are in Chennai. The Chennai, we have the northeast wind. So there are two direction of the wind. So this is north, this is south. Right. So the wind, mostly the southwest wind will be there. Sorry. Yeah. So mostly the southwest wind will be there, and the second one is the northeast wind. So these are the two wind seasons we have it. So currently we have in Chennai, we get only the northeast wind, and western coast will get the southwest wind. Sometimes we may get the western wind also, we get it. So like the Kaitar and other location, we get the western wind. So most of the time we get the west direction wind, and other as well as northeast wind also we get it. Right. So this is the characteristics of the wind, and yeah. So the wind generation. So you know that already I explained to you. So when you are generating electricity from the wind, so no pollutants, right? It's a clean energy, no pollutants like carbon dioxide, sulfur dioxide, and nitrous oxide. It is also no need of cooling water, and also indigenous, no need to compete with the other rest of the world, right? So advantage of that is the wind generation. And compared with the fossil fuels, the cost to supply constraint feature, and cost supply constraint, it is there. So where we will get it, how we'll get it, in which country they will supply. Currently we are getting coal from Australia most of the time. And also environmental problem is there, and we are using the fossil fuels, then already explained to you. And the resource assessment, right? So whenever you want to know the resource, we have to assess. How do you assess the wind resource assessment? Because the wind turbine, just look at here, this is the wind turbine. So the wind turbine, the main fuel is that the wind. So without wind, the turbine cannot generate electricity, cannot start rotate and cannot send electricity, right? So the wind is the main fuel. So main fuel means we have to assess. I have told you that wind is not the continuous resource, it is the variable resource. Then we have to assess where the wind pockets are there, where the wind resource which is available. Even the previous slides have shown there the map which shows only the western coast and other places only we have the wind, the western side, right? And other side, the northeastern side and all northeastern side, northern side, the wind speeds are very, very less compared to southern directions. The western coast, right? So then we have to assess. So how do you assess? The wind resource assessment means the quantification of the wind resource to compute parameters such as average, what is average wind speed, average wind energy density, and the average annual energy production. Right. So this also, I do not want to go for it in detail. I'll just go for it. So wind rhythm in India. So yeah, previous slide, just I'll explain to you also. So the how much power available in the wind. So the wind is even though it's a less substance, when the wind flows, which has energy, that energy is called the kinetic energy. And the difference between the power and energy, the power is nothing but the rate of doing work. Yeah, just a minute. So it's not writing. Yeah. So power is nothing but rate of doing work, right? Work is nothing but energy by time, and energy is nothing but it's a kinetic energy by time, right? The power is a power equal to kinetic energy by time. It means that when you want to calculate the power, the how much amount of kinetic energy which passes through this surface per unit time. So that's called the power, right? So the kinetic energy formula, half mv square. Here the m is nothing but the mass flow rate, which depends density, area, and velocity. When you apply to this equation, then we'll get the power available in the wind energy equal to half rho a v cube. It means that power is directly proportional to the velocity cube. So this is the basic formula you should know. Everybody should know when you are learning about the wind energy, the power available in the wind equal to half rho a v cube. So this already I told you, May to September brings the best wind, and November to March is a very low wind. Right, this is the regime of the wind. So this is, the passes, right? So the Tamil Nadu has a God gift. We have the three different passes. So the three different passes. One is the Aralvaimali pass in Kanyakumari, and in Kanyakumari district we have it, Nagarkoil and Kanyakumari, and the Sengota pass in the Tirunelveli, and the Sengota, and Palkat pass in Coimbatore. So these are the region. So which has, so this is the range of hills. The range of hills, in between the hills we have the gap. This is the gap will be there. Sorry. So in between the gap will be there. When the wind comes in between these hills, what will happen? The wind becomes skewed, and the exit path will have the high wind speed. For example, in case here we have the 5 meter per second, the exit path will have the 8 meter per second. So just like when you walk between the two buildings, then what you will get the same effect. So when you are outside, you will not have much, higher wind speed. Where just when you walk between the two buildings, you will feel that is a higher wind speed, right? When you are taking any papers, then it will take away from you also if you are not holding properly. So that is a tunnel effect. This is the gift of guard. So this already explained to you. So now I'll come to the turbine. So components of the wind turbine. So wind turbine which has more than 8,000 components, right? In which the major components only we are going to discuss. The major components are the rotor, right? The rotor which comprises of the blade. You can see the blade. The blade. So the blade, this is called the hub. So these two portion, hub, the hub and the rotor called the, hub and the blades are called the rotor, and the drive train. So the drive train which will be inside of this, the closers. So the drive train, I will explain to you. Then tower, and also the control system will be there to control the entire turbine, and the yaw system will be there to make the turbine moves towards the direction of the wind. And this is the nozzle when which protect the environment, right? So this is the structure, exploded view of the nozzle structure inside the structure. Just look at here. This is the rotor. The rotor is connected to the shaft. This is the main shaft. This is the main shaft as well as the low speed shaft. And here we have the gearbox. So here we have the high speed shaft. Here we have the generator. And so this is the next component is that's the blade. Okay, so the blade. So the blade is which is required to extract energy from the wind. So the blade only which faces the wind, right? So the blade generally which is made up of different materials like the glass fiber, carbon fiber, and organic aramid fiber. Mostly it is being generated, it's being manufactured from the glass fiber only. Okay, so glass fiber, whenever need, so they will go for carbon fiber. The carbon fiber, the manufacturing of the carbon fiber is it's not much easy, and as well as its strength is very high compared to the glass fiber. But the carbon fiber, the cost is enormous, right? Very high cost compared to glass fiber. That's why the most people they use only the glass fiber. And whenever they need the more strength, like this is the root portion and this is the tip portion, they will use carbon fibers also. Right, just look at here the blade. So blade. So in India, the largest wind turbine is 5.2 megawatt. Now it has come to 5.3 megawatt. But in the world, the largest turbine is 25 megawatt. 25 megawatt, one single turbine. Just imagine it. Even for 5 megawatt of wind turbine in our country, the rotor diameter is the rotor diameter means this is the rotor diameter is 160 meter. 160 meter, and hub height is 120 meter. 120, beyond that also. And other turbines are the lower capacity turbine. The hub height is even for 3.3 megawatt. The hub height is around 140 meter, and the rotor diameter is also 130 meter. 130 meter, right? But in the world, the largest turbine, right? So this is the world largest turbine, which has the hub height of around 300 meter hub height. Just imagine it, 300 meter hub height, and 280 to 300 meter rotor. Hub height, and the rotor diameter also it come greater than 300 meter, like 330 meter. Just imagine it, how big the turbine is there, and how tall the turbine, and how large the rotor diameter. So it comes around two cricket grounds. One cricket ground comes around 130, 140 meter. It goes more than two cricket ground. Just imagine it the size, how it is possible to transport. So it is not possible to transport on land, but it is possible to transport on the, mostly for the sea surface. So that's why the larger capacity of turbine can be installed only in the sea surface. See, this is the additional, the blade how they are transporting from one place to other place. And the drivetrain. So now we have seen the blade and the purpose of the rotor. So just you can see where I have seen, I don't know. Yeah. Okay, so that is the exploded view. The exploded view. And the next component is, yeah, so here just look at here the hub. So hub which connects the blades, right? So hub which connects the three blades, so it has some portion to connect, right? And here just you can see the hub with the blades are called the rotor. So rotor is coupled to the shaft, main shaft. Okay, just look at here. Here the turbine. I mean the hub and the rotary hub and the blades are here, and some of the turbine, the blade which connect to the hub. This is a hub. This is a blade. The blade which connect the hub through bearings. So this is called the pitch controlled turbine. Pitch controlled turbine, right? So the pitch controlled turbine means it means that the blade can adjust itself, it's an angle, so that so that what it can happen, it can at low wind speed try to get the maximum energy from the wind. At a higher wind speed to limit the speed, it means that reduce the speed. So that is the purpose we are using it. For example, so this is a power curve, right? This is a power curve. This is the wind speed versus power, right? For example, this is the 5 megawatt, 5000 kilowatt, sorry, 5000 kilowatt. At I can say that at rated wind speed, it can generate, for example, 13 meter per second. It can generate 5000 kilowatt. At 5 meter per second, it can generate 1000 kilowatt. And for uh, 7 meter per second, it can generate 3000 kilowatt, right? So this is there at 13 meter per second. Whenever it reaches 13 meter per second, it can generate 5000 kilowatt. So you can see here, then already I told wind speed will increase with the height, right? Wind speed will increase with the height. Even the wind speed increases, the power has to increase. But what it says that because of the pitch control mechanism, which controls the pitch angle and it adjusts the pitch, so that what will happen, the power is limited. So power always be constant even though wind speed increases up to 25 meter per second. So the 25, when it reaches the 25 meter per second, the power will drop and the turbine will shut down. So this is called, that is the power curve. The power curve which describe the difference describe the relationship between the what is the wind speed, what will be the corresponding power, right? So the drivetrain. The next one is the drivetrain component. So the drivetrain component is the complete power transmission system, which transfer the power from the kinetic energy from wind to electrical energy. Okay, starts at the rotor hub, ends at the generator. You can see starts at the rotor, ends at the generator. So that's called the drivetrain components. Now just look at here the drivetrain. So already told this is a hub which connects the blade, 1, 2, 3 blades. So 3 blades which connect. When the wind contact on the surface of the blade, blades are generally the aerodynamic shape of the blade. It is not like our fan blade, which will be the flat section, but this is the aerodynamic shape of the blade. Every places it will be the aerodynamic blade. So just look at here. Here the aerodynamic shape. This is the aerodynamic shape. When the wind hit on the surface of the blade, and their blade is aerodynamic shape. So what will happen? It's create the lifting action. So lift, the two forces which creates. One is the one is the lift force. Yeah. So the one is the lift force. Yeah, other one is the drag force. So this is the drag force, right? So due to the lift force increases when the wind blade, when the wind hits on the blade, so entire all three blades will start lift. The lifting action is happening. They start rotating. So since the blades are start rotating, uh, here the motion which converts the linear motion of the wind converted into rotary motion, because the blade the rotor start rotating. The rotor is coupled to the shaft. Since it is a low speed shaft, even when it starts rotate at 10 rpm, the shaft also rotate at 10 rpm. One moment. Yeah. Okay, yeah. So here, yeah, yes, correct, right? So when the blade, right, when the rotor start rotates at 10 RPM, the shaft also turns at 10 RPM. But our generator, which needs 1000 RPM, for example, depends on the number of poles. So 10 RPM to 1000 RPM, I have to step up the speed. So when I want to step up the speed, I want to place here the gearbox. The gearbox which step up the speed from 10 RPM to 1000 RPM. So here we have the high speed shaft. The high speed shaft also rotated to 1000 RPM. So these are the components you should know, before you want to make the digital twin. You should know about what are the different components are there, and how it's functioning. So that's why then I explained to you here too the function of the wind turbine, and this is the heart of the wind turbine. Right. So here, the generator will generate electricity. We can evacuate power from the generator to the grid. So that is various other mechanisms also it is there. And the gearbox, then I told you that. So different types of gearboxes are being used, and so this gearbox, the function is to step up the wind speed. So other component is the so other component is the controller system. The controller system controls the turbine. So already I told one type of control to limit the power, and other system is to stop and start whenever the emergency comes there, and the control system immediately swiftly act and protect the turbine. So first one is the safe and the protections, right? That the two functions that the two function of the control system. So the control system generally will be on the top of the nacelle and as well as the bottom of the tower. So here the bottom of the tower will be the main controller will be there, and the top of the nacelle, the inside the portion, the control system will be there. Control system. So it is the slave controller. The slave controller which receives all the information from the different sensor, and this one, it passes to the master controller. The master controller which controls the entire turbines, right? The master controller which controls the entire turbines, that is there. And this is the control system. So how the wind turbine which works? So when the wind contact the surface of the blade, the blade start rotating. When the blade start rotating, the shaft also start rotate, which couple to the hub, I mean the rotor. And when this is aerodynamic efficiency. What will happen here? The linear motion is converted to rotary motion. It means that kinetic energy is converted into, here we have the shaft and the gearbox. So gearbox we have it, kinetic energy is converted into mechanical energy. From here the mechanical energy is converted into electrical energy. So this is the energy conversion which is happening in the wind turbines. Okay. So this is this I don't want. So this is the wind turbine technology, different technology options like aerodynamic principle, the vertical axis wind turbine, vertical axis wind turbine, horizontal axis wind turbine, different power control options, the stall control turbine, variable pitch control turbine, controllable aerodynamic surfaces, yaw control system, active stall regulation. So these are the wind turbine technology options are there, and different yaw orientation, whether it is facing towards the wind or facing, opposite sides of the wind. And yaw orientation, driven yaw, free yaw. Driven yaw means driven by the motor, and free yaw is without having any mechanism, automatically turns, but which has the van backside. The rotor position, either it is the upwind position or it is a downwind position. When the rotor faces towards the wind, it's called the upwind position. When the rotor faces back, the rotor faces the lee side of the wind, that's called the downwind turbine. And type of hub, either it's a rigid hub or it is a tethered hub. So sorry, this is for a two-bladed turbine. This also for two-bladed turbine. This is the wrong figure. The number of blades, either it is one bladed, a two bladed, three bladed. So two bladed system will have the two tethered mechanism. Two blade also which has the tethered mechanism, right? and rotor speed, constant speed, variable speed turbines are there. So this is, in general, so just what I want to say here. So mostly most of the countries, they are following the horizontal axis wind turbine. The advantage of horizontal axis wind turbine, see the horizontal axis wind turbine, when the wind hits on the surface, start rotating, generating electricity. And the advantage is that already I told you, when the wind speed will increase with the height. The advantage is that whenever you want to raise the height, and you can increase the blade length, when you want to raise the height, increase the blade length, the rotor diameter will increase, so that power also can be increased, because power equal to half rho A V cube, right? The area is depends, right? The power is directly proportional to the A. When the area increases, the power also will get increases. So that is the advantages. The disadvantages, whenever the system gets any failure of generator gearbox, then when you want to bring it down, then you cannot generate electricity. That is the disadvantage of the horizontal axis wind turbine. And this is the vertical axis wind turbine. So vertical axis wind turbine means, the turbine the turbine can rotate at any direction. That is omnidirectional. The advantage is that one. Other advantage is that all the drivetrain components I told you, so shaft, gearbox, generator, everything can be kept it on the ground. So that is the advantages. Disadvantages, many are there, and onshore, the disadvantages in this turbine is that you cannot increase the height because the buckling can happen there. Increase the height. The world largest turbine is a 4 megawatt, but I don't know whether it is running or not. But horizontal axis wind turbine still it's reaching 25 megawatt currently. Then it goes to 50 megawatt, one single turbine. So that is the other advantages and disadvantages in this one. So when you are placing wind turbine in the land, that's called the onshore turbine. When you are placing wind turbine in the sea, called the offshore turbine. So this is the both. So because when you want to make hydrogen, you can use either the onshore turbine in the offshore turbine, but mostly various European countries, they use the offshore offshore wind turbine, because the offshore wind conditions are good. So the high wind speed will be there compared to onshore turbine. And also you can go for largest wind turbine. So currently 18 megawatt has been installed commercially. So 18 megawatt, 10 megawatt, 14 megawatt, 15 megawatt, 16 megawatt, 10 megawatt, and 18 megawatt of turbine can be installed in the offshore condition. You can generate enormous amount of electricity from the offshore conditions in the sea surface. Yeah, so the pitch control, I told you that, so the pitch controlled means each blades can be pitched separately. That is independent pitch control system. The pitch control means the turbine can pitch its own axis. It can change the angle. Like, the pitch motor is there. Pitch motor can activate the blade. The blade can rotate its own axis. Because of this mechanism, the blade can rotate its own axis. Since it's rotated its own axis, it can adjust the angle of attack, and it can also the blade angle, so that it can adjust its, the power and various, the stop purpose also can be utilized. So this is the yawing mechanism. So yawing mechanism means the entire rotor and the nozzle can turn towards the direction of the wind. Can go when the wind comes, it will be there in the towards this direction. When the wind comes in the opposite direction, the entire rotor can rotate. You can see there, entire rotor can rotate in the other direction. So that is called the yaw system. Just you can see here, this is the tower top. This is the tower. So you have seen there, this is a tower. On the top of the tower, we have the tower top mechanism. This is just looks like the gears. And you can see the many number of motors, 4 to 6 motors will be there. So these 4 to 6 motor can turn the wind turbine towards the direction of the direction. Just imagine it, the total turbine weight will come around thousands of tons. So thousands of tons of weight, the entire rotor can turn it. Just imagine it how a massive system of the wind turbine and also the marvelous of the wind turbine. Right, the tower and the foundation. So the purpose of the tower is to upright the entire structure and also give the stability of the entire turbine, because the turbine which works, the turbine which works in different wind conditions. So that the tower has to hold the heart of the turbine. Heart of the turbine is the drivetrain, right? The tower has to hold the entire turbine and also withstand the entire load. So one day the low wind speed will be there, another day high wind speed will be there, another day storm or typhoon like of wind speed will be there. So all this wind condition, the turbine should not get buckled, and also turbine should not get uprooted. The tower structure should withstand the entire system. So different types of tower also can be used. I do not want to explain. Now come for the wind farm layout optimization. So how to optimize the layout? The optimization of the layout is nothing but how to place, where to place, and what is the distance between the one turbine to other turbine I have to give, and which direction I have to place the wind turbine. So the group of wind turbine is called the wind farm. For this is the simple grid, one turbine back, another turbine we have placed, and just look at it, this is the optimized layout. So here, just look at here how the layout is being optimized. Okay, so where I want to place, where I can get the maximum energy from the wind. So that kind of location I want, and also I have to leave the space for the road, transmission line, because and also the house and the inhabitants location. So beyond that location only, we have to follow the regularization. The regularization it will give where to place, how to place. Accordingly, we have to select the site and place the wind turbine. That's called the wind farm layout optimizations. Now come for the digital twin of the wind turbine, right? So just look at here, what is the digital twin? So previous class also might have heard the digital twin is nothing but it is it is the replica of the object, right? So the wind turbine is you can just look at here. This is the physical assets of the wind turbine, and so digitally it's replicated. So digitally it's replicated, that is a replica of the turbine. So here what it gives explanation about how digital twin technologies, which is revolutionizing the wind energy technology. So I have already explained the various components. So digital twin can be done the components wise also, like previously explained to you, the rotor or single component of the blade, drivetrain system, or towers. So these are the systems are there. And when the system relies on the data source. When you want to make the digital twin which needs the data sources, the data sources can be obtained from the SCADA system. The SCADA system means supervisory control and data acquisition system. The supervisory control data acquisition system, it may get data from every 1 minute, or it's a 10 minutes, or it's the 5 minutes. And also the central monitoring station system, there we can get to the high frequency and weather sensor data also. And the digital twin application is to performance the monitoring. Why you want to do the digital twin? Because I want to perform to check the performance of the entire turbines, and also other applications also I will explain to you. And also fault prediction. So fault prediction, where the fault it's going to occur, how I am going to attack. But currently what the turbine we have it, so we not have the old turbine like 200 kilowatt or megawatt class of turbine. It is not possible to make such a kind of application. And the latest turbine, I told you, the offshore turbine, even 15 megawatt and above, 13, 14, 15 megawatt and above. So they have the digital twin technology. So the digital twin technology continuously, it's interacting with the turbine, the physical structure, and it's verify the performance. So once it's verify the performance, if the performance goes, then you will check and it's doing the optimization. And also the virtual sensors we have it. So virtual sensors we have it. So now just you understand it. What is a digital twin? So digital twin is which creates a virtual replica of the wind turbine, virtual replica. So you can see the turbine and virtual replica of the wind turbine that operates in the real time condition. That operates in the real time conditions. And also this also gives the definition of the digital twin is that so virtual representation of a physical object, not only object, process or system that serves as the real-time digital counterpart throughout its life cycle. So that's called the definition of the digital twin. So this digital twins also have three different models. So that is the physical entity. So the physical entity which is equipped with the sensor and actuators, right? Three components. The digital twin which has three components. One is the physical entity, virtual model, and data connection. The physical entity which connect to the real world assets. So physical entity which connects the real world assets. The physical entity which has the sensor and actuators, and also the data generation, and the virtual model. The virtual model which contains the digital replica. So the digital replica, which contains the simulation engine and analytical platform. This is the in general, right? And data connection. So data connections which gives, connect the bidirectional flow, and which gives real-time synchronization and feedback loops. So in general, the formula for digital twin equal to physical assets, virtual model, and continuous data exchange. Continuous data exchange, that's called the digital twin. So here another explanation. This is the core definition: a dynamic virtual representation of the physical object, process, or system. Characteristics compared to other digital system is that here it is connected via real-time data sets, real-time data, and also which allows to mirror the physical state of the system and simulate the feature states and provide the insights. So that is the most, so compared to other digital system, the digital twin, the main characteristics is that which connect the real time via real time data system, right, which allows to mirror the physical state, whatever the state in the physical, just it mirrors the same state and simulate the feature how it will be there. So that is the characteristics of the digital twin. It is not just a 3D model which gives the live simulation. So live simulation, can we make our body the real time digital twin? It is possible to do it, but if you are placing the instrument, the sensor to get the informations, right, get the information, then it is a possible system. So three distinct level of digital representation. So digital model. So the digital model. So you have been talking about the digital model. So digital model which gives manually the data sets, right? So that is a digital model. And so digital model which has the physical object, and which gives the manual data transformation. Digital shadow. So digital shadow, it can give the digital data, but the only one direction only. You can see the turbine and the digital instruments are there. The digital instruments can transmit the data to the storage system, but it is only one way only. It cannot be other way. But the digital twin system, it can talk both way, both the digital system and as well as the digital object as well as the physical object. So that is the advantages of the digital twin system. And so this is yeah. So this is the key components of a dynamic data flow of a digital twin. So key components, there are 5 different components are there in the digital twin system. So one is the physical entity, already explained to you. So different physical entity will be there. This is actual set of the system. Second one is the communication. The first one is the physical entity, so which connect to the environment also, the physical entity and the environment. So environment, so physical entity is there, for example, wind turbine. Wind turbine is placed in any location, and environment means different environmental temperature, pressure, humidity, it will vary. And the Kayatars, in case if you are in Chennai, the wind, the temperature and humidity will be different. When you are there in Tirunelveli, it will be different. When you are in Gujarat coast, it will be the different. So the second component is the communication. How it is interfacing, the communication part which interface the digital twin. Yeah. So the communication part the communication part which communicate between the communication between these two system. And the third, the first component, the second component, third component is the digital twin. So the digital twin which contains access control, we have to give the security. We cannot just like that to give the access to everyone, right? The second one is the human machine interface system. The human face interface visualization, AR, VR, user interaction, and the other system is that methods. The calculation methods, the functionality, and the simulation system, different calculation methods, and data storage places, and finally the event generation. These are all called the digital twin system. And this is the heart of the system. The digital twin is the heart of the system, is the access control, human machine interface, and for the event generation, calculation methods, and storage system. And finally, then it interfaces with the cloud system, the associated services and the data processing system, right? So this system, the leverages of the cloud-based system, right? So finally, just it interact the entire system, and finally it goes to the application part. Application part, it can be anyone can be there. So it is the analytics, machine language, right? And it will provide for the decision support. And this is the continuous data exchange. How it is a continuously data exchange? This is you can see the physical entity. So the physical entity which contains sensing technologies, like the many sensors will be there in the turbine, and at different places, it will be placed at different instrument, and reverse engineering, and also the image measurement, and just you can see the particle sensing technology. So this particle sensing technology is the to capture the correct state of the system, current state of the system. The particle sensing technology which capture the current state of the technology, right? So this physical entity which interact with the environmental system, so environmental mapping techniques are there, and virtual model system, right? The CAD software, computed fluid model, and even for the bladed software, and various other CFD software, and also which talks to the services, and also which talks to the data. So data means which have the historical data, the existing data, the current data set, which all, so this continuous data exchange system will be always be there. That's why it's called the digital twin. Is better, it is a trend of the existing trend of the wind turbine system. And this evaluation, you can see there 2010-20 how it is evaluated, and 10-15, initially it was set in 2002, and 10-15, the instrument comes for the IoT system and the sensor proliferation, and 15-20 it comes AI and ML integration. 2025 now it is in the autonomous system. So the system which contains this evaluation of digital twin technology, so which integrates the various sensors, like the IoT sensors, and right, and the cloud computing system, AML system, 5G, 6G system. This is, currently, previously it was 2G, 3G, 4G. So now it is the 5G. So the 5G network, it's a good amount of communication. It's communicating from the physical entity to digital twin technology. And now it is going to come the 6G. So it is a ultra low latency, very quick communications, right? You might have used the 2G, how it was there, then 3G. So when it comes to 3G, then you said, oh, it was good. So 3G, then you changed your mobile to 3G. Then again it's a 4G. 4G, the data transfer was extraordinarily good. So then 5G, now with that unimaginable, the 5G, the data transfer, right? The next it's going to come for the 6G. Just imagine it, the fraction of second you can download the data sets. That's we need for data transformation from the digital twin to the cloud. So the cloud data transfer should be every seconds, right? The edge computing system is the local system of the computer system. So this is the wind turbine digital twin architecture, which has the physical layer, communication layer, data layer, model layer, and application layer. So these are the, when you want to design your system of digital twin, you should know about all these things. What the physical layer which contains? The physical layer which contains the entire wind turbine. That's why then I explained to you what is the wind turbine, what are the different components are there. So that's why then I said the resource assessment. The resource assessment also which gives information about we collect the wind speed, direction, temperature, pressure, and humidity. So this is the environmental sensor and environmental sensor like the humidity, temperature, and the pressure we have to measure it. And the actuator system, it's the actuate. The SCADA system will collect the entire turbine's instrumentation details. What is the temperature of the gearbox oil? What is the strain of the blade, current status? So everything just we can get it from the physical layer because we place the instrument at different location. Just it's the communication layer which communicates, which it gets the information from the physical layer through wireless sensor, satellite communication, and turbine control interface. Then this is the data layer, which the SCADA data, meteorological data, which stores the data set. The data layer which stores the data set. Whenever we want to get the data, we can get the data. And the digital twin system, which is each always talk to the data layer. What was happened the previously, last year, the previous year, and what is the current status. So what it can be in the future also, it can predict by using the data layers. Model layer, so we have to make the model layer, the aerodynamic model, structured model, predictive maintenance model, and the simulation models. The application layer, so it's monitoring. The main purpose of the digital twin is that we have to monitor the turbine wise as well as the wind farm wise. Why we want to monitor? Because I am the investor, I'm investing per megawatt, I'm investing 8 crore rupees. So then 100 megawatt, I'm investing for 800 crores of rupees. So 800 crores of rupees, ultimate aim is to generate good amount of electricity from the turbine, and also I have to get I have to get profit from the generation. So that is my main aim. So then what I'm doing, I'm monitoring. Why should I do the monitoring? Because I'm monitoring the entire turbine. I'm checking the performance, whether the turbine is performing good or not. Then I will take the decision what I have to do the next step. And also it just look the integration of the system also, right? So this is the framework of the system. Okay. So types of the framework also, just I'll do that. So when you want to do the design of the digital framework, so first yeah, the design. So the key factor which involves for the design of the framework is that data selections, right? So model representation, what model you are going to represent, physical integrate, how you are going to integrate the physical model, and which gives the influence of the, and also you have to, the system also has to talk to the expert decision making also, and what are the different team compositions, right? So this one, and digital twin application for maintenance. The digital twins, you can use it for the application of operation maintenance, because operation maintenance costs are enormous. We can reduce the cost by using the digital twin mechanism. And digital twin mechanism, the purpose is it will predict the maintenance, predictive maintenance. Okay, so now it is happening. Now it's happening. The small crack in the blade, wind turbine blade. So then immediately the system which says that now the crack has happened. So the signal will change. So then if you know that within an hour, within a minute or 10 minutes, you can switch off the turbine, and immediately the operation personnel can go and repair the blade, and within a day or two can be completed. Then you can start the system and can run. In case if you are not seeing there what happened, then if it is continuously rotating, the blade get the damaged blade get crack and propagate, and the blade get damaged and can damage also the entire system. To avoid such a thing, the digital twin will be better one. And also the cloud and IoT system. So for this, then already told you how to place, the sensors. From the sensors, we have to get the data, and from there, the communication should be there. The quick communication should be there, and also you can do the reliability analysis, the long-term performance, what will be the lifetime of the entire turbine system, right? So then final one is physics and neural network system. So these are the types of digital twin system. Either you can do the component part, or asset the entire assets of the single wind turbine, or entire system process, the integrated system, or it's a complete network system. These are the types of digital twin system. What is the difference between the traditional monitoring and digital twin monitoring? So the traditional monitoring, that that, so it is a reactive approach. So reactive approach, then we get the information, point in time snapshots. So point in time only can get the snapshot. But the system, the traditional monitoring system, is always the manual approach, manual inspection and manual approach, which relies only on the historical data, and the simulation can be only the limited simulation only can be done it. But you see the digital twinning advantages. We can the proactive approach. So this proactive approach, so it's integrated with the real time data and the insights. So just imagine it how the real time data mean weekly what is happening. For example, your body is there. So many of the old persons, for heart issues, some other issue, they keep some instrument inside, right? Some instrument inside. So then it always, otherwise they hold some instrument in hand. The pulse always will be monitored by doctors or some others also. In the system will be monitored. The same kind of system, only proactive approach. When you are getting the real-time data and insights, immediately you can, do the rectification and the live data. So that the predictive analysis, you can do it, and also you can do the advanced simulation. So now it is happening there. What will be in the feature that you can do the simulation itself, you can do it. You do not want to disturb your physical structure, because the physical structure is here, it's a replica of the physical structure. You can do the simulation in the physical, the replica of the structure, digital twin, and you will get all the information, right? Because of the digital twin, so the downtime can be decreased to 30 to 50%, and maintenance cost can be decreased to 25 to 40%. So this is a digital twin versus traditional monitoring, and which has the many capabilities. So the digital twin can do the monitoring and do the simulation, not emulation. It can do the simulation, and also it can do the prediction, what will happen in the future, and to do the optimization, and also the control and the collaboration with the multi-stakeholders. So these are the capabilities of the digital twin. The same, right? The simulation. So this is the entire simulation. I do not have the time. Madam, what is the next 10 minutes, right? Yeah. So this is the digital twin implementation. The digital twin data requirements are, no, I have sure, quitted so many slides, right? Because of the time constraint. So data
Yes,
requirements for the digital twins, real-time sensor data. So that you need always the real-time sensor data, and also you need the historical operation data, real-time sensor data, right? And also you need the historical sensor data. Real-time sensor data means already told temperature, pressure, humidity, and as well as the turbine sensors, strain gauges, temperature from the gearbox, the temperature from the nacelle, temperature from the generator, right? What is the vibration? Vibration sensors will be there, and various other sensors, right? Historical operational data, what was the last 1 year, 2 year, 3 year, 5 years data set, and also the design engineering data sets, right? So design engineering data, the baseline, including computer aided model, computer aided design models, and the specifications and various other data sets, and the maintenance record. What was the maintenance record? What was happened? The log the previously. What is currently happened? And just we can check and predict, and also the environmental data. Data accuracy should be greater than 95%, and also completeness should be greater than 90%. So this is the timeline is every second, less than 1 second is well and good. So these are the data requirements for when you want to do the digital twinning. So you need, these are the data sets, right? So you cannot do immediately the entire system of the digital twin. First you have to start from the digital twinning from the your component. First you have to start from the component, then you should move, right? So modeling approach, either you can use the physics based model, data driven models, and the hybrid model. Different standards you have to follow. So this is aerodynamic model, the blade element momentum theory, which gives this model you can do it. Otherwise the structural digital twin, the entire structural digital twin you can do. And the power performance monitoring, right? So the power performance monitoring, you have to check to the power curve measurement. So this is my expected, this is my expected power curve, this is the actual power curve. So this is the warranted power curve. So already I told you the wind speed versus the power, and the wind speed versus power. So when the turbine manufacturer, they sell the turbine to the developer develops the turbine, they give the warranty. So warranty means, so this is my turbine generally used to generate the power, but when the developer, they wants to get to know what will be the my current power generation. So we will do the power curve verification, do the testing, then the difference between these two, then they have to make the penalty of this one. So power performance comparison we can do. And in case if it is doing the underperformance, we can check so whether it's a blade damage has happened, or the pitch miscalibration is there, or yaw misalignment is there. The complete fleet comparison also can be done. Which turbine is generating low wind energy? See, I also have the experience of that. So one of the wind farm was generating low amount of energy. So there we have seen some of the turbine is generating good amount of electricity. Some of the turbines are generating low amount of energy. If you have the digital twin technology, so then you could have addressed it earlier time. You can the address in the earlier time, and you can address it, because now currently in the some other case also it's going on. So in order to avoid these things, if you have the digital twin, then it give the better technology options, right? So the entire wind farm also can do it, because I'm skipping these slides. And so now the last 1 or 2 slides, I'll talk about the green hydrogen. See, now you have seen there wind turbine. So first we discussed about the wind turbine, different components. Now how we can make the wind turbine, the physical assets to the digital twin model. Now by using this digital twin model, how you can generate the hydrogen, right? The hydrogen, right? See, this is nothing, it is the same technology only. So generally the hydrogen is being produced by using the different technologies, but mostly the electrolysis. The electrolysis, water electrolysis, the electrolysis, when you are using the electrolysis, it is being separated hydrogen and oxygen separate, right? Hydrogen and oxygen separate. But we need the power. So the power is being obtained from the wind and solar energy, or biomass, or some other. When you are using this green energy to generate hydrogen, that is a green hydrogen. So the green hydrogen will have the storage also, can be stored. Okay. So when you are generating green hydrogen from this green energy, it generate zero carbon emissions. And also it's complies with the Government of India definitions, right? So this I do not want to. So the system approach of hydrogen, you know. So National Hydrogen Mission, our honorable, Prime Minister Sri Narendra Modi ji announced green hydrogen will be the basis of green growth through green jobs and setting an example for the world towards a clean energy transition. So the government wants to already 500 gigawatt from the green energy. So 140 gigawatt from the wind, 200, 300 gigawatt from the solar, and for other biomass and green hydrogen, geothermal. So these are all combinations. So combination we should reach 500 gigawatt by 2030. So this gives the Make in India program, so the global hub for green hydrogen production, and also achieves energy independence by 2047. So 2047 is the 100th year we are going to celebrate our independence. So in the 100th year, we should have independence, achieve energy independence. We should not depend on other countries. So currently we are depending, like, I said, the coal we are, importing from Australia, and for petroleum products from Middle East country and in Russia, and sometimes in America also, right? And we should have the independence. That is our vision. Right. And also reduce foreign exchange outflow for energy imports. So energy from, the same only in the exchange outflow from energy imports create sustainable jobs because the enormous amount of jobs are there. So this is the setting an example for the world towards clean energy transition. This is the 2030 target, 60 gigawatt from the electrolysis capacity. So that is the government of India, and the 5 million metric tons of hydrogen has to be produced and should become the world leader. Why we can become the world leader? Because enormous amount of renewable energy resources are there. By using the renewable energy resources, we can generate, produce green hydrogen. The green hydrogen we can export. How we can export? So you can see there. So you export to the other countries like, the Australia and India, like Chile and other tropical region country has enormous amount of solar and wind. So this can be generated and export through hydrogen to the other countries like, Europe, Japan. So these are the country which needs, and various application can be utilized for this green hydrogen, like the fuel for transport application, building block, and oil refining, and various industries also being used this green hydrogen, like, steel industry. Yeah, so the steel industry they are using it, and various process also being used for this iron and steel. Yes, iron and steel refining process they are using it. Green feedback they are using it, right? So there are different types of hydrogen also. Green hydrogen means when you are generating electricity, when you are generating hydrogen, when you are producing hydrogen from the green energy, that's called the green hydrogen. And the blue hydrogen when you are generating hydrogen from natural gas, that's called the blue hydrogen. However, in the natural gas, the blue hydrogen is that even it's generating carbon emission that will be captured, but it cannot be mitigated, but it can be captured a certain amount. Gray hydrogen, the carbon dioxide will be emitted. It will be, it will goes to the atmosphere. So that's called the gray hydrogen. So now you know the difference between the green hydrogen, blue hydrogen, and the gray hydrogen. So this is the difference, right? So this is the water electrolysis. Hello?
Sorry for the
Hello?
disturbance, sir. Sorry. You can
Yeah.
proceed, sir.
Yeah. So now I'll finish another
Unmute
5-10
பண்ணுங்க.
minutes. Yeah. So water
Yeah.
electric process. So different, water electrolysis are there. I do not want to go for electrolysis process. So this is the general you may hear from other lectures also, right? So this is the water electrolysis process. Then water, the water anode and the cathode will be there. And when you are giving electricity to this, and it is, it's separating the hydrogen and oxygen, right? So hydrogen can be stored in the bottles and can be kept it in the, in the storage yard, right? And also we can use it for electricity generation. So different storage system are alkaline storage system, proton exchange membrane, and a solid oxide electrolyte cell. The efficiency will be 70 to 90%. What is the other advantages compared to battery system? So battery system we can store very limited period only. But in the when you want to store in the hydrogen, you can store it in the long time also. So that is the advantages and the different applications. So currently, I know the 2 years back I visited Netherlands. So there, so they attended offshore wind and as well as the green hydrogen, but they already started using the green hydrogen because the green and producing the green hydrogen. They are also using this green hydrogen for transportation. Now they are planning to, make the pipeline for green energy hydrogen because they are producing green energy hydrogen in the offshore section. The offshore section from the wind turbine, offshore wind turbine, they're generating and transporting through the pipeline to the various locations. We can, later stage we can use the heavy duty transport also and power generation. The advantages in the power generation is that whenever we have the renewable energy, the intermittent sources, variable resource, wind and solar, it can generate the electricity whenever it goes down automatically for smoothing the grid. The power which goes from the green hydrogen to the grid, so that the grid always will have the same capacity. Right, so this is the wind hydrogen. Wind hydrogen, I don't want. So, and also wind forecasting. So just look at here. This is the wind system, wind hydrogen digital twin system. So wind. So this is the wind farm, right? So the wind farm, already I told you the digital twin. So the digital twin, the wind farm digital twin, which completely monitors the wind farm and also the predicting the wind and also the predicting the feature of the turbine state. So that is the digital twin of the wind farm. Now we are integrating into the electrolyzer and the storage system also. What is the storage? Currently, what storage we had, what pressure we have it, and the electrolyzer, what is the status of the electrolyzer? Make IoT sensor for each and every place. Just take the system and make the replica of the wind farm as well as the storage system and electrolyzer system, and also the grid system, entire grid system. Just make the replica of this one. Now make it do the forecasting. Right, we can do the forecasting. What is the hydrogen energy demand? So whether I want to do the produce or we can stop it. And what is the electricity price? I can, participate in the market. So participate in the market. So then the market, depends on the what is the energy price, whether it should generate or it is a closest not to generate, and how to optimization of the cost, generation, production. And also you can, monitor continuously real-time performance. What is the real-time performance of the entire system? What will be the efficiency tracking, whether it is a predicted efficiency or goes down? What is the degradation? Which system is getting degraded? Whether it is a storage system degraded, whether it's electrolyzer system degraded, or the grid system getting degraded, or the wind farm it's getting degraded. And control hierarchy, entire system is being control hierarchy, so that we can the wind farm and can generate electrolyzer system and the individual stacks. So digital twin optimize the wind hydrogen system, which increases the hydrogen production by 10 to 20%. Just imagine it, if you do not have the digital twin system, the 10 to 20% will not be there. So offshore system, I do not want because only time is up. So offshore system, so this is the offshore system. The structure will be there for making the green hydrogen storage system, right? Here you can see offshore wind, the platform. Wind turbine will be there. Offshore substation will be there. Offshore substation. So then you can generate, produce a hydrogen. The hydrogen will be transported. So this is the solar system. So that's all. And feature wind turbine technology, it can be enormous. We cannot imagine it. It's a larger rotor diameter, thermoplastic plates, the recyclable, already recyclable has come, floating offshore turbine, it's already there. Superconducting generator will be there. So already told various technology, even 6G systems, 6G. So all this combined, we can generate a good amount of this one. So this is the digital twin evaluation happened. So this is the feature vision, fully autonomous system. This is the feature vision, fully autonomous wind farm with human oversight only. Just you can see oversight. First install and come back. That's all. So various research opportunities are there. So materials, recyclable blades, digital twins, real-time optimization. So many of them are trying to get digital twin for wind farm. We can try, but to start from the wind components. So I mean, that is the conclusion. Just I'll conclude it. So now, just to sum up, so we have discussed. So just I have explained to you. Yeah. So it is disabled by the post. You can just switch on my video also, right? So conclusion. So final conclusion: the wind energy. Just the wind energy is the critical for India's 500 gigawatt of renewable energy project. So wind energy still it is there. So we installed only 54 gigawatt. The government expect to go for 140 gigawatt. So still we have 90 gigawatt to go. So in which 40 gigawatt from offshore and the remaining 40 gigawatt, 50 gigawatt from the onshore. So enormous jobs are available, and also digital twins enable 10 to 30% improvement in energy reliability costs. So wind to hydrogen GAM, this is the game changer for energy storage and sector coupling, wind hydrogen. And so we do various other activities. The Ministry of New and Renewable Energy, they have the separate division for green hydrogen, right? So this is so what you can do, so just for my side is that in future, so renewable energy and as well as the hydrogen. From renewable energy, we are going to produce the hydrogen. So you can integrate this system into your curriculum also. Renewable energy, one of the renewable energy previously when we studied, so it will be the wind, solar, biomass only, 1 or 2, 3 units only will be there. So now you can add the green hydrogen also, initiate research. So many research are going on and build industry partnerships. So that is the best way to do the research, right? Yeah, thank you. And so just I want to thank for the, Dr. Kalevani ma'am and all the staff members and also the management of the college. And also I would like to thank for the entire participants listening the lectures. Right, so nearly 130 participant. I don't know whether how you were sitting for the more than 1.5 years. Okay, anyhow, I want to thank you also for that, right? So thank you, ma'am. Yeah, I
Yes, sir.
hope I have given
Yes,
I
sir.
have taken a little extra time also. So if you
Really,
have any time, if you have any question, then please ask me. Sorry, ma'am. Yeah, please go ahead. Yeah.
yes, sir. Really well structured and thought-provoking session, sir. We truly appreciate the valuable knowledge, expertise you have shared with us. Actually, my research area is wind energy conversion system. I completed my PhD in that area, but majorly I concentrated on generator and power electronic converter side, where I have granted with a patent. But you
Great.
have clearly, I could say, you have opened our eyes that we could steer our research direction towards wind, hydrogen, and digital twin technology. Really, very eye opener. I hope all the participants here could steer their research, that is their PhD, towards this direction so as to enhance their performance as well as they could contribute to the society for greener hydrogen or a green energy system. Thank you so much, sir. Participants, any other queries?
If you have any question, you may please ask me.
Participants, any questions? Sir
Yes.
Karthikeyan, sir.
Yes, someone has asked regarding why don't we go for vertical axis. Then I have clearly explained the vertical axis wind turbine has the limitation. We cannot go for higher capacity of the turbine also. So that's why the better system is that three-bladed and horizontal axis wind turbine. Yeah. Any other
Karthikeyan,
question?
sir, now you can pose your question, sir.
Sir, it was a wonderful presentation from your end.
Thank
So
you.
my
Thank
question
you.
is, what is the minimum velocity in which we can operate these modern day wind turbines, and what is the maximum limit up to which it can function without any difficulty?
Yeah, see, the minimum wind speed which is required to turn the turbine rotor and generate electricity 3 to 3.5 meter per second. So that's why every designer which is design, they start generating electricity 3 to 3.5 meter per second. But generally we do the design of the wind turbine. It depends on the location, depends on the wind speed. For example, the class 1, class 2, class 3 turbines are there, even class 4 turbines also there. So class 1 turbine means the 50 meter per second the maximum wind speed. So 50 meter per second recurrence of 50 years. So based on the extreme wind speed, based on this we do it and multiply with 1.4 safe draft factor, then it will go for 70 meter per second it can withstand. So generally 70 meter per second mostly will not be available, right? Even for it comes for our cyclone, it goes even maximum in the Varda cyclone, we faced 40 meter per second. So 50, 60, it's rarely can occur. But that kind of location, when you're doing the design, we check it. But in India, mostly the class 3 turbine, the class 3 turbine, the wind speed is 7.5 meter per second, 10 minutes average wind speed. And the maximum wind speed is 37.5 meter per second. So the turbine is designed to, so even the wind speed is there, the turbine is turned off at 25 meter per second. 20 to 25 meter per second. So generally 25 meter per second, because beyond that the wind speed time will be very, very less. So then operating and beyond that turbine means then we have to have the good stability of the entire wind turbine. That is not required. So that's why we do the always optimization of the wind turbine design, right?
Yes, sir.
I hope I have
We call
cleared,
it a
right?
cut-in and cut-out speed, right, sir?
So also I have another question, sir.
Yeah, please.
Which type blade configuration is proved to be most efficient as on date, sir?
Which type configuration? Yeah.
Yes, sir.
You want the generator or it's
No, blade, sir. Blade, sir. I'm just asking about the wind blade.
No, wind blade, you're asking wind blade, the horizontal axis, you're asking?
Sir,
No,
rotor.
not about axis, sir. I'm asking about the blade aerodynamics. Blade
Angle you're asking, right? Yeah. See, generally the blade angle should be 0 to 30 degrees, the better optimization. Blade angle. Okay, 0 to 30 degrees is the better optimization, better we can get. It depends on the angle. When you want to go for a 70 degree, the 70 degree means that you can do maintenance, and the 90 degree means you turn off. Okay.
What is the optimum gear train ratio, sir? Speed ratio?
I can't say that. Gear train ratio depends. Whether you are using the parallel shaft gearbox, whether it's a planetary gearbox. So planetary gear means 1/3 of size you can reduce it. See, it depends on the size. See, I have the RPMs. The larger rotor diameter will have the 5 to 6 RPM, and the rotor generator which needs the 1500 RPM. Now just look at about it. What is the ratio you need? 1:100, 1:150, and the number of stages you can reduce, whether it is one stage, 2 stage, 3 stage. So instead of going for 1 stage, 2 stage, 3 stage parallel shaft, you can go for planetary gearbox. So mostly 2 stage to 3 stages, or 3 stage to 4 stages, right? So 3 to 4 stages mean 3 stages. You can have the epicyclic gear train. Planetary stage gearbox. 1 stage go for the parallel shaft gearbox. So that will be the good one.
Solid, sir, there is one more question from a participant called Ramalakshmi. How can we differentiate IoT-based system from the digital twin?
Without IoT system, you cannot do the digital twin. IoT that is the basic sensor system. So sensor system means so you have to have the sensor. Sensor means you have to place each and every location the sensor. Sensor gives the data. Without the data, I cannot make the digital twin tech system. Yeah. Any other question?
Any other questions, participants? Okay. Thank you, sir. Thank you so much.
Thank you. Yeah.
May I
Thank
now
you all.
invite? No, sir.
Yeah.
Just a minute, sir. May I now invite Dr. D. Periyar, sir, to propose vote of thanks.
I would like to
No, Mr. Ilango, please unmute now.
Sir,
I would like to express my sincere thanks to Dr. K. Boopathi sir, National Institute of Wind Energy, for delivering session 4 as the part of AECT Atal sponsored faculty development program. The session was highly informative and insightful, and it greatly enriched our understanding of the subject. We truly appreciate the time, effort, and expertise shared, which added significant value to the program. Thank you so much, sir. Thank you for your valuable session, sir. Thank you once again.
Yeah, thank you. Yeah.
Sir,
Thank you all. So
sir,
somebody others
we
also have
have
raised some
session.
question. Then you may also just you can send email to me or you can message to me also. Yeah, thank you all.
Sir, stay online, sir. We need to take a screenshot.
Okay.
I request all the participants to turn on your camera, please. Dear participants, please kindly turn on your cameras.
The all-new Seltos, badass forever. எத்தனை டென்டல் ப்ராப்ளம்ஸ் கவலைப்படாதீங்க ஏசி வாரிசு கோல்கேட் டோக்கன் இங்கிருந்து ஃபார்முலா இது ஜோன் பீட்டா போல போராடு வந்து 3 மடங்கு சிறந்தது இதுதான் பெரும்பாலான நீங்கள் மற்ற விஷயங்கள் பாதிக்க முடியும் அடடா அவர் அதை தடுத்திருக்கலாம் கோல்கேட் டோக்கன் டென்டல் ப்ராப்ளம் தொடர்ந்து தடுக்கும் This season at Kalyan Jewelers, enjoy up to 1,500 rupees off per gram on brand edition. Conditions apply.
Okay.
Yes,
One
sir.
second, sir.
Thank you. Thank you, ma'am. Yeah, I'm leaving now.
Thank you, sir. Thank you so much.
One second, ma'am.
மற்ற participants mute பண்ணிடுங்க.
One second.
அந்த விஷயத்த அருங்கிட்ட சொல்லி பாப்போம் அவன் தான் எப்படா என்ன சீண்டி பார்க்கலான்னு இருக்கானே டீ கடையில வச்சு ஜாட மாடி அவன் ஃப்ரெண்டு கிட்ட பேசுற மாதிரி என்ன சொல்றான் யாரையோ தட்டு எடுக்க போறியாமே அவன் குழந்தை பிறக்காதா ஏதாவது பிரச்சனை அவனுக்கு டாக்டர் போய் பாடுறான்னு என்ன அவங்கள பத்தி பேசுறான்பா
Thank you to your participants. Please unmute. Please mute your cameras.
Thank you for the cooperation. We'll meet tomorrow. Thank you.
Thank you, participants. Thank you, dear professors. We will meet you tomorrow evening 6 to 9:30. Thank you for your valuable time.
பொறுத்து பார்த்தோம்ப்பா ஒவ்வொரு அடிக்கடிக்கு தப்பா பேசிட்டே